stakeholders from varying corpus of society, so governments, industry, non-for-profit, academia. And this is what Mila does best in a sense, bringing all of these players together. My hope is that these discussions today really act as project ideation workshops, and that real collaborations, new collaborations ensues and turn into real application for climate mitigation or adaptation. And I just want to, I'll be brief, I'm done. I just want to thank the many teams at Mila that came forward to put this event together. And of course, the many organizations who agreed to have a representative on our panels. And thank Anna Vartanian for the special effort she put into creating this event. Thanks all, have a nice day.
Thank you so much, Stéphane. Merci beaucoup, Stéphane. I will invite David Rolnick on the stage for the keynote address. David, the floor is yours.
One moment for the technical setup. Cross our fingers. We hope. Yes, excellent. It's great to see everybody here today. From so many different sectors, so many different stakeholder communities. Really looking forward to conversations with all of you. Is there a... Can I take this? Okay, great. That way I don't have to be bending down all the time. So I am going to be giving a really, really fast overview of some areas in AI and climate change, just to try to motivate the discussions today and kick us off. There is a lot of work in AI applied to climate change. We wrote this big compendium paper a few years back, which is still pretty relevant, looking at all of these different areas, from climate modeling and prediction to buildings and cities to transportation, agriculture, forestry, and other land use. And if you're interested in understanding 100 pages worth of specific ways that AI can be used to help fight climate change, I encourage you to check out this paper. What I want to talk about now, though, is why we're not there yet, why we still have to have these meetings, and why there's a need for places like Mila, and in collaboration with all of you and so many other communities, to move the needle forward. Why haven't we finished solving the problem of AI for climate change? Despite the fact that there has been considerable attention and attention given to the potential of AI for fighting climate change over the past few years. Despite all of this attention, why can we not just use AI and solve lots of climate problems? And the answer, I think, is that despite the fact that everyone in the world is now talking about AI, for better or worse, the kind of work that's being done in AI is not the same as the kind of work that's needed to make a difference on problems in climate change and in related areas as well. And to frame that, I want to draw a distinction between two different paradigms that one can go about AI innovation. The first one is sort of the standard paradigm for how a lot of AI gets conceptualized and innovated upon. And that is so widespread that we don't even really question it often within AI and tech. And that is to build bigger, more general algorithms. Algorithms that perform well on benchmark data sets, that are designed for a stereotyped set of metrics, some particular notion of accuracy, some particular notion of loss. And the goal is to make them as problem agnostic as possible, for them to be useful across every problem. And by developing them in conjunction with massive data sets, the idea is that the bigger the data, the more general the algorithm. That, unfortunately, does not immediately lead to impact on many climate-relevant problems, on many other problems. We're seeing in climate and healthcare, elsewhere across the applied AI ecosystem, that oftentimes the fanciest, newest AI tools are being beaten still by regression or random forests. And that is a huge shock to many in the tech community because these AI algorithms perform really well across the benchmark tasks. And yet, that is not enough. And so I'm here to highlight a second paradigm of AI research, which has already been pursued for years, for decades, in many user communities, and many communities within the AI space, but really needs to be highlighted more and prioritized within mainstream AI innovation. And that is application-driven innovation, focusing on real-world tasks, the particular challenges associated with those tasks, and the metrics associated with them, not just designing for some standard notion of accuracy and loss, designing for really what the user needs, building in domain knowledge from the user community, from the domain of application, and building use-inspired methods. And this is complementary to methods-driven innovation. They're not separate. We still need that blue sky AI innovation. It's just not enough to try to solve all the problems at once, because sometimes when you try to solve all the problems at once, you end up solving none of them. And I think that this interchange between these two modes of innovation is really the future of AI, both because ultimately we don't just want algorithms that sound cool, we want algorithms that help society. And we also want, as computer science researchers, we'd like algorithms that solve interesting challenges and are broadly interesting and relevant, not just ideally to a particular narrow application. We would like to have more general innovations. But actually, by thinking narrow, we can often end up with those general innovations, because thinking about specific problems often means that we come up with cross-cutting innovations to tackle challenges like out-of-distribution generalization, interpretability, lightweight models, physical constraints, limited label availability, multimodal data, and many others. These are the challenges that we often face if we think about the particular user needs in a domain of application. And by innovating narrowly, we often end up innovating broadly. So that's the call that I want to issue, and something to bear in mind, I think, throughout the day. Think in terms of how to design for the specific needs of the user, how to design for impact, not just assume that impact gets handed to you on a plate. So I'd like to discuss one example in depth and then go very quickly through some other examples from our group here. The example that I want to touch on is motivated by remote sensing for agriculture, although we'll find it's broader. And here, we're working with partners NASA Harvest, European Space Agency's World Cereal Program, and others. And the challenge is that climate change is greatly affecting agriculture around the world. Some of the biggest impacts from climate change are related to food security, and governments around the world are looking for tools to help them intervene to manage risk for the agricultural sector and related sectors as well. Now, how do you do that? You need to have information to guide decisions, and oftentimes that means turning to satellite imagery, which is widely available. We need maps of where crops are, what their yield is predicted to be, and much more. And to gather those maps, we need to process data at scale. And machine learning has increasingly been turned to as a way to process vast amounts of satellite imagery, to create maps like this, which was created by NASA Harvest for the government of Togo in response to the need by the government of Togo to implement agricultural policies to guard farmers after COVID. So how do you actually use machine learning for remote sensing in agriculture? Well, it turns out there are actually very significant challenges. The first one is there's very limited labeled data. If you look at the orange points here, that's where we have data on what type of crop is there. That is very, very sparse. We don't have information for most of the world. The labels are not what you would expect in standard computer vision algorithms, where you would imagine every part of your image has a label. In fact, somebody went out to the field and labeled one point. That's the kind of label you have. Point, 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 point. Very difficult for a standard computer vision algorithm. And then the people who are implementing these have a very limited computational budget. I could be talking about a digital divide or differences in resources between different countries, but that's a bit misleading. Most of the Canadian government agencies also have a very limited computational budget. They certainly don't have access to massive GPU farms. So we should think in terms of very limited computational infrastructure in general. And so how do these different paradigms of innovation perform here? Well, methods-driven innovation would not really work very well. It would be using it would say, let's take a standard computer vision tool designed for ImageNet or some other massive data set, and let's use it for these images from satellites. But that would not be able to deal with these challenges: sparse labels, irregularly shaped labels, and a limited computational budget. Gosh, the latest computer vision algorithms for classification are extremely large. So let's take a look at application-driven innovation. And let's think of limited computational budget as something that we're trying to design specifically for. And let's think of all the different domain knowledge that we can build in from satellite imagery. And the information that we can build in includes geographic structure, because these images aren't just provided to us on a plate, they are provided to us with geographic information associated with them, metadata. And there's a lot of unlabeled data as well, not just these data points that have labels. And then also there's a diversity of different sensors and features coming from any particular satellite. Let's combine all of those and come up with a use case informed algorithm. And so quickly, as an overview, since I realize people are coming from different backgrounds, I want to mention what an encoding is, or data representation. A low-dimensional data representation is something that you've probably seen in different forms. PCA is an example of this, and with deep learning, people are interested in auto-encoding versions of this, where you take an image, for example, you throw it through a neural network, get a compressed representation, and then try to decode that compressed representation with another neural network back to the original. The point of this is that you have a compressed representation which captures information from the inputs, because the inputs can be recaptured from that compressed information, and then that compressed representation can then be used in many other different contexts. A version of autoencoders that's become particularly popular is masked autoencoders, where you remove part of the input so that you can actually be robust to noise. You can reconstruct the input even if there's some noise. And we're going to build on this framework and design something that is specifically for remote sensing data. And here we're going to use the structure of the data, many sensors, many points in time, and we're going to use self-supervised learning with an auto-encoding framework where the goal is to predict different time points, predict different sensors using only a limited set of data. And the point of that is that it becomes both robust to different kinds of inputs. If you don't have all the data, you don't have all the sensors, you don't have all the time points, you maybe just have one sensor, one time point, it can reconstruct the rest. And also, it's very reusable. So it is pre-learning a data representation that can then be used across lots of different downstream tasks because it's self-supervised. And so the way you might use it is you would train this full algorithm, and then you would chop off the final piece, the reconstruction part, and you would use that learned encoding for task 1, for task 2, for task 3, with a very simple classifier like linear regression at the end. And because it's a simple classifier, it's usable for a lot of different stakeholders. And so I'm not going to go into numbers here, but suffice it to say that we're performing above or at state of the art, not just, it turns out, for agriculture, but for so many other different things as well, because there hadn't been foundation models which had been designed for the structure of remote sensing data. So we found that this relatively simple approach, Presto, can outperform vastly more complicated, or bigger, I should say, algorithms in the context of agricultural mapping, assessing fuel moisture to assess wildfire risk, tracking trees. In certain limited cases, we'll see more detailed tree work later, measuring algal blooms, and other tasks as well. And this is a comparison of the number of trainable parameters. Compared with the vision transformer, Presto performs as well or better, and it has orders of magnitude less parameters, which translates to much cheaper computational cost. And just for reference, this is what you would see if you compared this to a large language model. If you asked ChatGPT to solve this problem, of course it would give you complete nonsense because it's not designed for anything like this. But suffice it to say that this is where I think that AI should be going. Smaller, smarter, more impact-driven models rather than trying to solve all the problems at once and not actually solving any of them particularly well. Okay, I can really quickly touch on a few other examples. We also work on, how much time do I have? Okay, I have like a couple minutes more. We also work on biodiversity monitoring, filling gaps in biodiversity data. There are enormous gaps in where biodiversity data is distributed, as you can see by this map. Huge gaps across the global south, but also gaps across any part of the global north outside of population centers. How do you fill those gaps? How do you do biodiversity assessment if you're looking to, for example, get impact assessment for development in an area, work out which areas to protect? You need to be able to scalably assess biodiversity. And there aren't enough observers to do that, so we are assessing biodiversity from satellite imagery, being able to pinpoint exactly where we think that certain species may occur on the basis of the habitat information. And so we can get a species list predicted for a particular location using satellite and environmental data. This is work led by Ms. Zantang over there. And we can also incorporate data on some species to improve the predictions for other species. The goal here is that certain species are well observed, certain species tend to be very poorly observed, and how do you fill in the gaps? Well, you can use whatever data you have, and we have new data completion algorithms that can fill in those gaps. We also work on speeding up climate simulations. Traditional climate models are very accurate, but very slow. They can take months to run, even on supercomputing infrastructure. So there are a couple of different approaches which you can use to speed them up to get more localized and actionable predictions. And one of those is to approximate parts of the physics-based models. We approximate radiative transfer in particular, which is an especially slow part of standard climate models. These algorithms actually incorporate domain physics in order to make them more effective. This is being integrated into Environment and Climate Change Canada's models. This is work led by Zavel Kachai and Venkatesh Ramesh. And then we also work on increasing the resolution of weather and climate data, so taking super resolution algorithms and making them work in the context of climate and weather. They actually don't work normally in the context of climate and weather. So here where you have data that's coming in from a weather or climate model and you want to actually make it be more precise than 100 kilometers resolution, which you generally do, you can run it through one of these algorithms, sort of enhance the resolution of the data, and you can get much more precise predictions. And these can respect physical laws, and they can actually achieve arbitrarily high resolution with zero-shot generalization, thanks to some innovations introduced by our group with Paula Hada and Qidong Yang. And then finally, actually, I guess I have 2 more slides, but I'm running out of time, really. So we also work on materials discovery, both property prediction of how effective a new material is in a particular application. We focus on electrocatalysis, so synthesizing hydrogen, for example, green hydrogen, and also suggesting promising candidates for new materials so that you don't have to try all the possibilities. You can both quickly evaluate one and you can get suggestions on what to try in the lab. Not a replacement for experimentation, but it does reduce the number of experiments. And then we also work on power grid optimization, and there are a bunch of other projects I don't have time to talk about, where we're solving non-convex optimization problems, which are hard to solve fast, and we can ensure that they are both well solved and don't violate the physics of the power grid, which is necessary to ensure that you don't have a blackout. These are just some examples, but again, I want to highlight the key throughout all of these areas is really think about the use case, build what is needed within the particular context in which it will be applied, and cross-sectoral, cross-disciplinary collaboration is absolutely key in every one of these areas, and I'm looking forward to hearing a lot of talks that really highlight that today. So thank you to all of you for listening, and thanks to all the great folks that we've worked with to make these projects happen. Thank you.
Working? Yes. Actually, David, would you have a few more minutes with us? We're a bit ahead of time, and
We're ahead of time. I feel like I was not that fast.
No, you were perfect. You were perfect. But we just have a few more minutes before we jump into our fireside chat conversation. So if you have a little bit of time and if you have questions, we would welcome any questions you may have.
I also have plenty of extra slides. I can dive into more detail on any of these topics.
We could have 2 hours, I'm pretty sure, 3 hours of it. Any questions for David? I know it's right off in the morning, so it might not be easy to be the first one to ask the question at the conference. Yes, we have one question here. If you could just go on a mic here, that would be very useful. I can just give you a mic. Actually, let's do it that way. That would be much better.
Hello, David. Thank you for sharing the insights. I guess like a very outside of the box question, like what would be like one research that you would like to do in the field of AI for climate, but you think with limited resources, it's not tangible or it's not like the way to go forward, but you think it would be really nice to try that research out?
Well, I think that a lot of these areas are actually remarkably under-resourced overall, and that's for a couple of reasons. One is that there's a lot of money in AI, but it's not really going towards specific application-driven use cases oftentimes. Either that's because there is money for blue sky AI innovation and working on a particular problem just doesn't sound sexy enough, or because even within relevant areas of application and relevant partner communities, there is justified skepticism about the utility of AI as a result of people having tried general purpose things that don't work particularly well for them. Or alternatively, I think that there's increasingly a desire to integrate AI everywhere, but not really think carefully about what that AI means. And so that might mean let's have a chatbot, but it might not be let's think carefully about the problem that we're trying to solve. I realize I'm not quite answering your question, but I think that what I want to have more in this space is really thoughtful conversations between folks in AI and folks in relevant stakeholder communities, pinning down what particular users need. Now, of course, I have ideas about lots of different things and that different stakeholder communities benefit from, and we've seen lots of gaps, but I think that fundamentally the focus needs to be less on what is the biggest gap or what is the coolest thing, and what do you, for 1,000 different versions of you, need in your application.
Thank you.
We'll take one last question.
Thank you for the nice presentation. My question is about where can that type of research be done, and what are the challenges for our research institute? Because you're talking about communicating between different research connection, and sometimes our training of our students are not well prepared into the other field, and our institution ready for that type of research.
There isn't a need for computer scientists all to be experts in every other field, which is good because we're not going to be. There is a need for more computer scientists who bridge the gap with a particular other field, and this is advice that I would give in general for trainees, students in the room, that it is very useful to think about how you might look to intersect with one particular other field, whether that's agriculture, biodiversity, something else. There is a need for people who can build bridges between two specific areas, often. But I think overall, in our training of the next generation of researchers, there is a need for less hubris. The tech and AI communities often come in thinking that our tools are going to save the world, and they certainly haven't done that yet. They're so far arguably making it worse. I can talk about that in more detail if you're interested, even from a climate perspective. And there are several parts to that, and one of those is that there often isn't the time in computer science and machine learning. One doesn't teach often the time to listen and focuses just on building things. And the most important part about building things is knowing what to build. And so really teaching listening, teaching how to work with people in other fields is really important. And I want to, often the areas that I highlighted here, there is actually a lot of respect for them in the machine learning community typically. But if you get to social sciences, a large fraction of machine learning people don't even believe the social sciences exist, frankly. And there are so many applications that require input from stakeholders who are systemically disenfranchised within the machine learning community. Or there's the idea that we can just tech our way out of answers that fundamentally have to involve experts in how society works, whether that's in policy, whether that's in economics, whether that's in other forms of social science. And so like really having a wide tent of who the computer science community listens to is really important there. And building skills for sort of systemically cross-stakeholder projects. And then one more aspect, which I want to touch on, which is there needs to be more engineering support. Both data engineering, back-end, and front-end. One of the lessons which we can draw from the huge amount of interest in tools like ChatGPT is that something that has a shiny front-end is really, really useful to people. But that's not just applicable to ChatGPT. If every one of the tools that was being built in this institute had as shiny a front end as ChatGPT, I can guarantee you there would be orders of magnitude more interest in those tools. And that would be good, because right now people are asking ChatGPT to do everything, including things that it's not suited for. You can argue that some of that is the fault of the way in which it's pitched, but also it's, you know, a success story which we can learn from, and we can think in terms of if we build more user-friendly tools, that will help our tools be actually better used. And then a huge component of any innovation process in an application-driven area is also engineering because of data challenges, because of setting up the infrastructure to perform machine learning. All of those challenges are not things that researchers are generally well-equipped to do, but there are skill sets that one can build for those aspects of a project, and one can create more capacity in data engineering, research engineering, and really build that together with research innovation, because without the engineering support, the research innovation is going to be much more driven by whatever problems the engineering has already been done for, whether that's because ImageNet was already built or because there is a nice API that enables you to interact with this particular use case. So I'll stop there. Thank you very much.
Thank you so much, David. We're right on time. Thank you very much. Thank you for your questions as well. We welcome them through today, so don't be shy. Ask any questions you may have. Thanks again, David. I think we can give another round of applause, maybe. I would have loved to have a 2-hour session with all your slides today. So let's jump into our first part, Energy and AI, with Jean-Simon Venne, CTO of Brandbox AI. And Pierre-Luc Bacon, core academic member at Mila. So it's going to be a fireside chat. I will let you discuss, but if you have any questions afterwards, feel free to use the mics here and there.
Hello, everybody. Thank you so much for being here. I'll be moderating this session between Jean-Simon and Pierre-Luc. It's really a pleasure to be here today for this first session on reducing greenhouse gas emissions from buildings. Oh, thank you. Here's the final mic that we were looking for. So for those of you who know, and for those of you who don't, reducing emissions from buildings, greenhouse gas emissions specifically, is a crucial issue in climate change. And we have two excellent speakers here to join us today to tell us a little bit about that, both from the academic side and from the industry side. So Brainbox AI is one of Mila's partner organizations. Jean-Simon, I would invite you to tell us a little about the issue and about what Brainbox AI does to address this issue.
Yeah, thank you, Claire. I'm going to try to create a sense of urgency in terms of why you should care about building an HVAC, which is heating, cooling, and ventilation in these buildings. So really, when you look at the global picture, why are we in trouble and why do we need solution and innovation? There's three big drivers which are making our world not a great place when you talk about building. The first one is building, generally speaking, consume about 30 to 40% of the total energy of our planet, so it's the big driver. And the problem is this is increasing. So that pie has become bigger and bigger. Every month we're adding about the equivalent of Manhattan in quantity of building to that stack. So the pie is getting bigger and bigger. The second driver is the peak load. So unfortunately, we have the tendency to consume energy all at the same time because we all doing the same thing at the same time. So we're creating these huge peaks for the grid, and the poor grid manager or grid operator, they're stuck with these peaks, and they're trying to tell us that we should try to flat these peaks if possible, because when they're reaching the peak, unfortunately, they very often have to trigger basically oil or coal generation plant just to accommodate the peak, which is extremely bad in terms of emission. The third driver is a discussion that we started, Pierre-Luc, about refrigerant. And it's kind of a little dirty secret that nobody's talking about. So refrigerant are bad. They're really, really bad. It's these type called HFC, like hydrofluorocarbon, like nobody really understand. We all have them in our houses, in our condo, in our building. This is a refrigerant. And these refrigerant, they're really, really bad. So I'll give you an example, like a typical refrigerant that is used in a lot of different devices. It's what we call the 410A. And the 410A, 1 pound of that refrigerant, if it leaks out of your thermal pump or your heat pump, it's equivalent to 4,260 pounds of CO2. So you don't want that thing to leak out. And the problem is these refrigerants are increasing in usage. So we increased about the last 20 years, 45%. So we're using more and more of the refrigerant. It's because the planet's been getting warmer and warmer. So what can I tell you? We need to refrigerate more and more. But the worst part of it is most of our equipment, because they're not properly maintained or we're properly not managing them the way we should, they are leaking in between 10 and 30% per year. So next time you look at your heat pump beside your house, if you have one, think about, is it leaking or not? And really you don't know, because the only way you could know is like, it's funny, it doesn't reach the temperature the way it used to reach it. And that's because most probably you have a leak of refrigerant. So you should fix it because you're really not helping the planet. So these drivers need to be addressed. Brainbox is working a lot on the energy side to reduce the quantity of energy being used. But now we need to work on the peak load, and we need to start working on the refrigerant if we want to continue our mission.
Thank you. And Pierre-Luc, could you tell me a bit about the research, the applied research behind that? Because I'm mindful of what David mentioned about applied issues and how we solve those real-world issues. On the academic and the applied research side, can you tell me about what that looks like?
Yeah, okay, so thank you. So I think we started working together maybe 2-3 years ago or something like this. So I'm a researcher specializing in a field called reinforcement learning, which has to do with taking decisions over time. Our field has seen a lot of progress. I'd say one of the milestones was this system built by a Google DeepMind in 2012 that gave birth to literally DeepMind. And that was quite a milestone, because that's the first time that people were able to do reinforcement learning on high dimensional input, AKA pixels. And that's an example of a benchmark that allowed us to move forward and make a lot of innovation. But here's the thing that happened. We worked a lot on this. Google DeepMind was created basically around this to gather a lot of researchers. And I'll say that most of the questions we had to answer are now answered around this. So I've been facing a bit this existential dilemma as to, and my colleagues have been asking the same question too. Now that we know how to do this, what's next? So it's part of this kind of general thought process that I started working on more application-driven research, to really think about what is it that we do now. We know how to do high dimensional control. What's next? Yes, we can go get 1% extra on the benchmark in video games, but now what? What's going to be the consequence of that? So we started working together on optimal control for set point and demand response in HVAC systems. And that led us to do completely different kind of reinforcement learning, not the kind of reinforcement learning we're used to do in video games. And it's the same pitch that David gave us earlier, you know, by thinking differently, it also opens the, you know, whole wide variety of methods that are different than the one we're typically seeing in pure research with toy domains.
And what does that look like, the optimization of HVAC systems using AI?
So maybe
How does that work?
Just can maybe, you want to start? You go from the maybe application side, and I'll go with the opportunities in research, perhaps.
Absolutely, I will never go on that side of the equation. So basically, and it's funny because it's Yoshua Benjo that gave us the idea a long, long time ago, which is like, you know what, there's two very expertise in Montreal, which you combine them together, you get like extreme value, which is of course, you know, deep learning, all good, we all know that part, but don't forget operational research, which has been, you know, a center of excellence in Montreal for over 40 years. I was working in operational research back in the 80s at Polytechnique. We didn't have the computing power we were wishing to have, but now we have it. But if you combine these two things, you get a very interesting mixture. So what was the foundation thesis of BrainBox? Is like, we're going to get the prediction from the deep learning side, and if the prediction is accurate enough about what's going to happen in this room over the next few hours, and we really know what's going to happen in the next few hours in this room, we kind of see that future. Then we're going to use algorithm on the operational research side to try to find what is the optimal control strategy to make this room a better place in the next few hours. And it's a question of permutation of all of the possible control strategy, checking what is a prediction, multi-objective Pareto front optimization, and you then write back. You take control of the equipment to basically apply what you believe is the optimal strategy. And you go forward 5 minutes at a time, incremental side, 24-hour a day, 7 days a week. And then suddenly, you're moving from a reactive control strategy, which is all what you see in all of our building around the planet, to a predictive control strategy optimization. And then you start to shave like 10, 15, 20% energy on a daily basis in every room in this building. And that basically is the thesis of BrainBox. Now, how does it work under the hood?
Yeah, so I think what you've been describing is what we could be describing as model predictive control, which has been an important paradigm in optimal control. Now where we can make a difference in research is the predictive aspect, as you say here. So in model predictive control, what you do is you plan ahead a little bit, you try to imagine what's going to happen, and then you optimize with respect to what you're planning in the future. But you keep on doing this all the time. So even if you made a mistake as to what's going to happen, you're going to be able to readjust accordingly. So typically in optimal control literature, people have worked a lot on coming up with very good, sometimes physics-driven model. I think in domain of buildings, for example, the so-called RC networks are quite used a lot as a modeling tool. And it's important to say that we're not here to say we're just going to replace all the things you've been developing for the last, I don't know how many years. We're really there to embrace some of that deep knowledge that has been developed over time. And this is what we did in our collaboration. We used some of these physics prior and combined them with data-driven methods, aka neural LEDs. So I see Vincent here, I think is going to tell us a bit more about this. So I'm not going to go too deep into this. But this is to go back again to David's point. So why did we go for this hybrid approach in our collaboration? It's because we need to be smart about how we use data. We don't want to be exploring and trying crazy things. You know, we want to start from solid physics-driven principle, but then add on the machine learning data-driven aspect of it.
Absolutely. And one of the other essential points of this research that I should mention, because it is really a core value for Mila, is that it was done in an open source way. Can you tell us a bit about what that means for this research and what that means for climate research on a broader level? How does that feel to have been able to, and I'll direct the question towards Jean-Simon, to contribute to science, to open science, while working in industry?
Yeah, so there's 4 billion buildings on the planet. SAM, which is right there, we usually address the market as the infinite TAM. So the ocean is so vast that you could have about 100 brain bugs and still everybody is going to do very good. So what's the end goal here? The end goal is to save the planet, actually maybe save humanity, because I think the planet will still be here. But so we need a lot of brain bugs. So how do you make a lot of brain bugs? As long as brain bugs stay the number one, I'm good. You basically give the tool to others to follow or to innovate in their own path. And to do that, well, you need to publish and you need to give away what you just did. But you don't really care, because in this world of AI, the patent is kind of an obsolete concept. The rotation of our algo are moving so fast that by the time we would get a patent on an algo, it would not be used anymore. So we're very far from a new molecule in the pharma world. We're into a world where the rotation of innovation is going every 12, 18 months. So do you really care about a patent, or what you really care is to keep innovate faster and faster and move forward and stay at the lead front? So in that concept, like, why not make it open source, right? Why not that innovation that you put together be used by others so they could figure other things that you have not figured yet?
Absolutely. And Pierre-Luc, did that alter the way that you did your research?
So I think from the very beginning we established how it would be working. I think that's the key to success between collaboration between industry and academia. And you know, it's the first thing to know, and of course that's never been a problem with BrainBox, but when I work, let's say, as a professor with my students, we're not in a consulting kind of relationship, right? We're there to work together collaboratively from both sides to achieve something bigger that's going to be useful on both sides of industry, but also on the side of research. When you're a professor, when you have labs, when you have students to graduate, it's very important to be able to publish. So that's kind of key from the beginning, to be able to have results that we can talk about. And even more so in our communities, not publishing the code, not publishing reproducibility is a must, right? If you don't provide these things, well, people will think that first of all that maybe your results don't hold. So it's absolutely crucial, at least for the kind of work we do here, to be able to have whatever we present should be reproducible in some way. Now, in some way, that can mean a lot of things, okay? And this is where we've established a way of working together. We've been working through some simulation tools that we agreed upon, and we worked at this level. So that was the common interface between the two of us. Now, the way we chose to work is our students, for the complexity that comes with all the legal aspect, we're not working with the data, proprietary data of BrainBox. However, because BrainBox has actually very capable researchers, we were able to always be in contact with them, and on their side, they'd be able to run experiments, give us feedback on the data of their clients and so on, and would be able to keep on improving our model this way. And I think this is the model that I've been applying with other applied projects I have, and I'm working in drug discovery as well, and it's the same kind of pipeline and way of working that we've established, and I think that's the key to success.
Yeah, and if I may add, I think I saw Benoit in the room here. Like, are you here, Benoit? Oh, here, right in the back. The other Benoit. So Benoit was one of the first one we published a paper, and I could tell you, when you're a private company and you go to your board, you go to your legal department and say, we're going to publish. They look at you and say, we're not a university, Jean-Simon, like, what's your problem? So we really opened that door and said, no, we're going to be publishing. and we're going to be presenting, and there's going to be article, and yes, we will broadcast. And we call it like the Brainbox Lab within. I think Benoit was the first paper we published. Thank you, Benoit, for opening that road. It was not an easy one. It was then you were at Polytechnique, I believe, right?
Yeah, thank you. And I appreciate the way that you express that there is enough in the world for everybody. And if we're committed to making that impact, it doesn't matter if there are 100 brain boxes. And so it sounds like the ocean is vast. And in that vast ocean, there are, for sure, some unexplored areas. Can you tell me a bit about the future that you foresee for this greenhouse gas emissions reduction project, this sector, and what some of those unexplored areas might be?
Yeah, it's a huge ocean. I would think that probably the next big step forward is it's a grid optimization, and I think there's some talk coming up on this right after. So there's a huge opportunity there, like just shaving that peak, modulating that peak at the grid level. The impact on the emission is going to be huge, because if we could prevent that coal power generation plant in New Jersey to start at 2 p.m. in the afternoon in July, you having a huge impact, bigger than you could imagine. So how do you make that happen? How can you shave that peak? So that become like, again, another interesting AI potential solution. And then it's a refrigerant. And I'm trying to convince Pierre-Luc to work on a refrigerant. Lobbying happening in front of your eyes. So like we need to really tackle these leaks, because the leaks are happening and nobody really noticed. So think of the refrigerated truck. So with train technology has about half of the refrigerated truck on the planet. So this is all of these equipment you see in front of the truck, which is keeping the cargo at the right temperature. So think of vaccine, medication, fruit, ice cream, beef, whatever you're moving, it needs to preserve the cold chain. So these refrigerated truck, they do have leaks of refrigerant, and it takes time before you detect them, and then you're basically having a huge impact. So how can we make sure that as soon as we have a detection of a leak, we do something about it? And it's kind of seemed trivial problem, but it's not that trivial. You're gonna have like a huge impact. So that's another area that I think we should basically look forward.
Yeah, definitely. And on the research side, Pierre-Luc, challenges, opportunities?
Yeah, so the refrigerant part, so this is a separate project. We haven't worked on that one just yet. So, but Anna had this cool idea of doing material discovery. So we just started this. I'm really excited about it. But it's going to be for next year. If we have this event again, hopefully I'll be able to present you some results. But it's going really fast, and it's really exciting. Okay, I stop with this. Here's some other challenges, and we don't have a solution to that in research. So let's go back to temperature control, set point control, demand response or not. Here's the thing. If we do RL or any other kind of like smart data-driven method, as of now, it's very difficult to take the controller you learned and actually apply it to different building. We're not in a setting like in foundation models where you have one smart model that has learned everything that you can then fine-tune to different building. This is true in general of reinforcement learning. This problem of multitask learning or learning even from offline data is very difficult to do. And to me, the next frontier is kind of there, because the reality is that even if you have a lot of data, let's say you have 50 years of data, I'm gonna make stuff up. I don't know if it's possible to have 50 years of data in some buildings, but let's say you have a lot of data from one building. That's great. You're gonna be able to learn a lot of things. But the building next door, even though it might be very much related, very much the same, like look here, we have 6666 and 6650. They're pretty similar buildings, yet I'm pretty sure the equipment, let's say optimized from that one building, you won't be able to extrapolate anything about how it should be tuned in the next building. And this we don't know how to do. I mean, there's a lot of fundamental open research being done in RL on that topic. And but I think there's more to do, and I think being grounded in a real actual problem is the way to go, and we have one here. You know, the fundamental research on that topic being done right now in reinforcement learning is still on that one or two benchmarks, which I am so tired of working with. There are benchmarks, but you know, it's always, if you've heard of it, it's always MuJoCo, it's a simulated robotics domain. again, these benchmarks were useful at some point, but we've exhausted them, you know? So this is a great, great opportunity. And I'm gonna finish here with one last thing. We came up with this, I don't know, we discovered that the, maybe Vincent can help me, but it's the Department of Energy, whatever in the United States. I can't remember the acronym. They have this amazing initiative where they mapped out the entirety of United States, all of the buildings, and they all came up with machine learning models with digital twin of every potential buildings. You know, they used satellite imageries, they crossed out with, you know, records, taxes, and so on, and came up with digital twins of the entirety of the United States. That is an insane, you know, potential next challenge. Imagine trying to learn a model that can control and do well optimally across 125 million buildings, you know? So this is the kind of frontier that I'm after. And the pitch also, when we've been discussing with Anna, we should have the same in Canada. The project's called AutoBAM. We need an AutoBAM Canada so that we can also inform policies of what would be the impact of, you know, insulating our old houses in Montreal better? What would be the impact of this and that? Beyond also, you know, coming up with smart controllers, there are all these like building related questions that could be answered with such a data set that we don't have. But we have the expertise and we could totally do it. But we need collaborators for that. So this is very much ongoing thinking that we have. If you have thoughts, if you're interested about those topics, let us know. So that's it on the research side.
Yeah, thank you for that. And thank you for your enthusiastic call for collaboration, for connecting the ecosystem. It leads perfectly into my final question for you, because I want to make sure that we leave time for questions, which is, this has been the Mila Brainbox partnership has been a very valuable one. We've come up with some amazing applied research. You know, we've seen some concrete action there. And we certainly want to do more and encourage more industry academia work, but also multi-stakeholder, right, with the government and with NGOs, other organizations. So if you had a piece of advice for the audience and for the public at large to create those successful collaborations, what would it be? I'll invite Jean-Simon to start.
I would say don't try to innovate in your basement and try to raise a lot of money to hire all the people you need to innovate. Do it in an ecosystem. There is tons of different opportunity to team up and basically work in innovation and in kind of an ecosystem. View it as a cluster, an ecosystem, and then you kind of basically decentralize the innovation as having different people working on the same problem from maybe different angle or together, and then it fit back together at the end. And if we start to do that at a higher scale, we're going to become a war machine in terms of innovation in Canada. I mean, it's because we have all of the different components. It's just a matter of working together. And that should be easy, right?
I like the sound of that.
Yeah, I think that's it. Huh? It's essentially the same thing. It's finding the right people and of course being very much aware that we don't know everything about everything. There are excellent people with like tons of knowledge in like building science, and I have great colleagues at Polytechnique, ETS, and it's also a matter of finding the right students, right? So I was fortunate to be working with Vincent, but I don't think I would have been able to conduct that project without Vincent's expertise and without Vincent's co-advisor at the time, Anan Dagdogi, who's also an expert in those topics. So it's about knowing what you don't know. Now, I've learned a lot at this point, to the point, Jean-Simon, that I've gotten my ASHRAE card now. So I became a bit of an HVAC geek, but when I started, I didn't know much about this. So it's important to know what you don't know and find the people who know the things you don't know.
Absolutely. And I think at Mila, we're well placed in terms of talent to find the people who do know.
Yeah.
Thank you very much. And I'll open up the floor to questions. If anybody has questions, I invite you to either raise your hand so we can bring you a mic, or to come and stand up at one of the two microphones up here at the front to ask a question.
Merci pour votre présentation, c'était très intéressant. You mentioned that every building is different, so there's sort of an optimal control for every building. Is there also something to gain from trying to do it on a group of building, a neighborhood, or is that like, is the data too separated, or is there a challenge related to that?
I think there's work on the research side, and Vincent could tell you more, but on district level optimization. The question is like how realistic and where would that take place? There might be communities maybe in Europe where these kind of like policies can be implemented. I doubt that in Montreal we have that kind of like top-down control, but I think it's actively being researched, if I'm not mistaken.
All right, thank you.
Thank you. Any other questions? Thank you. I can come bring you the mic if you need.
Hey, thank you. So for me, the use of AI to optimize energy use is one of the most, let's say, concrete way to use AI toward sustainability. So that's the subject here. But since you have real-world data coming from your systems, have you already calculated the return on energy invested, like to confront the use of energy of your systems that aliments your data centers versus the energy that you have saved on your buildings?
Yeah, absolutely. It's something we're tracking, and we're doing that with, we're on AWS, so we're doing that in collaboration with them. So we basically figure out what's the consumption of energy we're doing in the cloud versus what we're saving in the building. Okay. So that's an equation that we're monitoring. And we are monitoring to a point that now we're like looking at the problem with the different cloud where they're located, and that's kind of information that AWS is giving us. You don't want to have a cloud in Australia. Like it's fascinating. We look at our different cloud, and I hope Benoit from AWS, I'm not putting you under the bus here. But basically, like we look at our different cloud in the US, Canada, Europe. The one in Australia is basically responsible for 94% of all of our emission on the cloud, one cloud instance, one region. So what we're going to do now is we're going to close it up and move to Japan because the Japan one is much better. So we're tracking that. In terms of energy kilowatt, yes, we're tracking that also. So we're basically offsetting. We're saying like, okay, we save you 15% that many kilowatt, but the cost on the cloud is X, so I deduct that, and then I basically your net gain in terms of energy saving. And the work we did with Pierre-Luc is quite interesting because the neural EDE in terms of optimizing, yes, the quantity of data needed to train a model, fascinating, right? The results are fascinating. But the quantity of energy to get the same prediction is stunning. So we reduce by more than half the energy of that model training to get the same result. So we're working in that direction too. So we're hoping that AWS do their job to make that cloud as efficient as possible, but we're also working on the tool you were using to make sure they do use and less compute. So we're becoming more and more efficient on that level too.
Okay, interesting. Do you publish the data? How much energy versus consume versus...
So is the question about the energy used for compute or the energy savings by deploying the policy in the building?
Yeah, energy for compute versus the energy saved by
So at least for the research we've done, the models are really, really lightweight. We're really not in the game of like training large language models on, thousands of GPUs. So, I mean, I think Vincent has been developing most of his research on his laptop, and then when it came the time to do hyperparameter optimization, might have launched it on the cluster. But these are very, very lightweight models.
Okay.
Negligible, we're not in the same game as large language models.
Okay, thanks.
Yeah.
We still have time, I think, for a question or two. Fantastic, thank you.
Excellent panel, thank you so much. I'm really intrigued by the question about building on open source. And since Brainbox has successfully raised from investors as well as gone through an exit process, I'm curious about whether building on open source ever created any friction in those conversations and how that was received by people that were taking a stake in the company.
Yeah, I'm going to be very careful because my colleague Sam is in the room and he's a legal background. Absolutely, a lot of friction, tons. Battle with legal, battle with everybody. But But when you start to explain what I was explaining regarding the IP, really, should you file for a patent or not, right? And it's really a race forward. So when you start to explain that and you show that, like BrainBox, I think over time, we had about 36 algorithms, but at any given time, we only have about 7 or 8 really in production. So we have a huge cemetery of algo which are dead, right? Like we bury them and said we put a little signs that this used to be an algo we're using. So, but that wheel is turning, and it's turning faster and faster. So the question is, are you gaining more by increasing your innovation ecosystem and yes, allowing basically publication and open source, than if you try to do it yourself? So how fast are you going to move that wheel, and then you're going to become the leader and win that race? Because it's a race. It is a race. It's a race which has the objective to save the planet, but it's also a race on the business side where you want to be number one and you want to capture the market. So, you know, do you want to go faster or you want to go slower? And then when you start to see it into that aspect, suddenly it makes a lot of business sense because you want to be the fastest and you want to be capturing that market. So of course there's a give and take, and why not? But you're right, most company will go like, are you crazy? I'm not going to do that. So we need to change that paradigm.
But at the same time, if I may just add, like I think open source software in AI, it's like this is the raw product. It's the raw material. It's unavoidable. I don't think any AI researcher can work with closed source tools. In fact, there are none. All of our tools, like, you know, PyTorch, everything, like all the numerical libraries, all of that is open source. But this is the raw material. It's not the refined product. The refined product is the thing that the company is going to own. It's a proprietary thing. It's about, you know, turning that into a gem, something that has value. But the raw product itself is not an issue. And in fact, our field cannot exist without that. So I don't think it's even a question. Now, there are licenses for open source that are problematic, and this is the only place where you got to be careful. For example, GPL licenses would require you to also keep the derived work open source, and that's often incompatible with companies. So it's the only thing where you got to be careful, but most like PyTorch and so on have permissible licenses, Apache and so on, MIT, and it's all good. So.
Yeah, I might add, when we did when Train made the acquisition over the last few months of Train, of BrainBox, we had to basically come up with a list of open source we were using, and we were a bit scared that Train might go like, whoa. But we had like pages and pages and pages. And no, I mean, they did bought it. So I guess it's good.
Thank you so much. If we have any other questions in the room, I'd take one more. If not, I would thank you for your wonderful conversation, for joining us here today, and I'll cede the floor to our next speakers.
Thank you very much for this excellent presentation. I'm happy to invite Vincent Taboga on the floor for a presentation, again on the same topic. Vincent, please come with us. Merci.
Hi everyone, happy to be here. So I'm going to present one of the work we've done in collaboration with BrainBox, and it was about developing data-driven models, namely continuous time models, for mainly controlling HVAC systems in buildings. And as Professor David Rolnick mentioned in the introduction, it's a thing to say when you're doing reinforcement learning research, or I'm not going to work on a Mujoko benchmark environment, but rather work on real-world problem. And it's another thing to design a problem that makes sense. And collaborating with industry help a lot with like the assumption you can make, what makes sense, and what in the end will be a really good problem to work on. And that was truly valuable to collaborate with BrainBox. So before diving into the solution, a bit of context that was mentioned before, but as you may know, in Quebec and in many places around the world, managing peak periods in grid is extremely challenging. And so I found this graph. It's the prediction by Hydro-Québec of the expected cost in millions of dollars of managing just the peak hours in the grid. And so we see this exponential trend. And having proper ways to manage peak times is extremely important. So there's different ways to approach the problem. The first one is say, if we need more energy, we'll just increase the production, right? But this strategy has its limit, and there's another way, which is to try to reduce the energy demand itself. And one tool we have to do this is to use what is called demand response programs. And basically, it gives financial incentive to people to reduce their power consumption at peak hours. But to handle this demand response event correctly, we need a proactive management to not affect the comfort too much. And so we framed all of this into a control problem where we want to control the temperature set points inside the building because this is what drives the HVAC power consumption. And what we want to achieve is first to maintain the thermal comfort in buildings because this is the primary goal of any HVAC system. But by doing this, we want also to limit the power consumption during these peak hours. And what we have at our disposal is a data set for a given building of the HVAC power consumption, the indoor temperature, and maybe some weather data related to the area. And with this data available, we've developed a prediction model. And the plan with this prediction model was to do planning and then search through the space of different possible set points to find the one that best suits both requirements of energy consumption and comfort. So one well-used model, it's in discrete time, and so it's through what is called recurrent neural networks. And so basically what you're doing, you can encode the state of your system in a latent representation that helps to gather like all the relevant information, and then do one step per one step predictions using this type of neural networks. And what we propose in this work is not to use discrete time models, but rather continuous time models. And these models are based on differential equations. And what they're doing is that they're learning this differential equation. And the main difference, if you compare the two graphs when the predictions are happening, is just that in our case we have this continuous signal that is the evolution of the power consumption and the temperature inside the building. And why we might want to do this is because oftentimes physical laws come as differential equations. So it already gives you the structure of the model you want to learn, and it will be consistent with the physics of the models. And so we're not relying fully on just the data to learn everything from scratch, because there's a lot of things we already know from our knowledge of the physics. And by doing experiments, we find out that in addition to being more suited to feed this prior knowledge about the physics, we find out that continuous time models are way more sample efficient. So in this graph, it's just showing the prediction error of both models. So we tested like different combination of both continuous time and discrete time. So it's why all the acronym stands for, but we don't need to worry about it too much. What you have to notice is that on the left are all the continuous time models, and on the right all the discrete time models. And the lower the dots, the better, because it's the prediction error we are looking at. And so in blue, we have the prediction of the indoor temperature, and we'll see that all the models are doing a pretty good job at predicting the indoor temperature. But there's a difference when it comes to the more challenging task of predicting the HVAC power consumption. And in a low data regime, where we just train the models with a bit more of 2 months of data, we see that the continuous time models are doing better than the discrete time models. And as we increase the number of data from the 2 months to 10 months, the gap is getting narrowed, but still having sample efficient model is key, because when you are to deploy this type of model in the real building, collecting data is often time consuming and expensive. So it's a really important aspect of the models. And these results are made on simulated data, but we tested also with the pipeline described earlier by Pierre-Luc, our models on real data. And this had also value to the research, because as you probably know, there's always a big difference between what happens in the controlled simulated world and the real world. And with these prediction models, just half of the problem was solved, because then we have to use it for planning. And so we developed a control algorithm that was looking at the impact of different temperature set points in the building to find this balance between energy reduction and thermal comfort. And so the goal was to maintain the power consumption at peak time, materialized by the black curve that happened around 6 p.m. every day. And the red curve is just representing the power consumption in the building, and so the goal was to keep this red curve below the black one during these peak hours. And we see that our prediction models were accurate enough, because in green it shows the set point change in the building. And so we were able to predict accurately enough the evolution of both the temperature and the HVAC power consumption to find these preheating strategies, where the controller was increasing the temperature before the peak to then lower the consumption at peak time. And it was like understanding how to play with the thermal inertia of the building to not affect the comfort too much. And so this is really the type of control we're looking for, and thanks to our prediction models that were accurate enough, we were able to find these strategies. So as a conclusion, maybe on the technical side, these continuous time models are really sample efficient. So it's a big advantage to compare to the widely used recurrent neural network type of models. And they are also more suited to include prior knowledge about the physics of the system. And I want to highlight, again, as a conclusion, how valuable collaboration between industry and academia is. First, to decide on problems that will make sense, and also to enhance the speed of both the quality of the research and the speed. And this is, I guess, a really key point, because there's a lot of problems to be solved. There's work for everyone. And so, time is running out when we're speaking about a problem that has direct impact on climate change. And so collaboration, I think, is the key moving forward. Thank you.
Merci beaucoup, Vincent. Now I'm happy to welcome Donna Vakalis, postdoc at Mila. Donna will join us online, but you can have questions for her as well. Donna, I see that you're with us. Perfect. The floor is yours. Let's go.
Hi. All right. Let me just grab my speaker notes. Thank you. Thanks very much. Okay, so today I want to talk about what happens when we stop thinking of buildings as static structures to be optimized and start thinking of them as living, evolving environments we can learn from. So the belief that we should be building more sustainably and learning from how buildings actually behave, that's shaped my work across research in my PhD and then in industry when I worked in the architecture industry and now in AI-driven applications at Mila here in Montreal, where I'm co-supervised by David Rolnick and Joshua Bengio. So during my PhD in civil engineering, I studied a wide range of buildings, old buildings, new buildings, schools, social housing, high performance buildings, and those undergoing retrofits. And a few winters ago, I was installing some sensors in an apartment complex. So there, the residents of the upper floors were opening their windows in the winter where it was minus 10 degrees outside. I think you guys can relate. But they're opening their windows not to get fresh air, but to actually cool down their overheating units, which despite the weather outside were really hot. They felt like they had no way to control the heat at the unit level, and the forced air system in the hallways was going at full blast, heating everything. So I give this example because on the one hand, you know, we have more efficient technology than ever. We know how to make efficient heat pumps, and it's pretty easy to buy a smart thermostat. And yet buildings, there's still this mismatch. There's still commonly a lot of wasted energy and still, you know, frustrated occupants. There's a mismatch here between expectations and performance. And this is like, if we really want to understand why buildings fall short, I think we need to look beyond individual components and start with the systems and assumptions. And I want to sort of highlight two major gaps that I've seen repeatedly. One is technical, but the other is cultural. And so let's start with the first. We, you know, in machine learning, we make simulations, and we know that the simulations can't capture exactly the messy complexity of real world buildings, but we have to simulate buildings, assuming things like fixed occupancy patterns or like very uniform, perfect comfort bands. And in real life, people move around unpredictably. The weather forecast is wrong. Systems age and change. And so even in well-designed buildings, you know, the performance can drift like suddenly or drift gradually over time, sometimes really substantially. And this mismatch is part of the technical reason we get wasted energy and discomfort and maintenance headaches, to name a few. But it's, you know, on the other hand, it's cultural as well, or even architectural. We keep designing buildings. I feel like I can pick on architects because I also have an architecture background. We keep designing these buildings that sort of like fight the climate and then, you know, maybe throw more technology at the problem to fix it. So we design buildings that, you know, normalize having an all glass facade, even in really hot or cold climates. And we normalize having sort of like 21 degree temperatures indoors in the middle of summer and reliance on constant mechanical cooling. And then we kind of try to patch it over with technology. These aren't just technical problems. They're really like cultural habits. So even though I am excited about the role of AI and climate, AI, as you know, it's not going to solve this if the core design itself is misaligned. And so I want to just take a moment to like touch on this to say, you know, where does AI fit or not? And so we've kind of said this part. It's not a fix for bad design or the goal in itself, but it might help us learn if we frame it as a tool for feedback and actually like a bridge between data and decisions. And that way it can, you know, it can reveal the patterns and discomforts, not just automate them, but help us make better decisions. So what we need really to understand where tech and specifically AI belongs in the built environment, I feel like we need to look beyond, you know, not just sensors and thermostats, those play a part, but we need to study buildings also as integrated systems. They're technical, they're human, they're social, they're messy. And if we want AI to support better buildings, we also need to think about, pedagogically, we need places that are real and occupied and messy, but still built for research. So this is why I'm here in part today, is to talk to you about this idea of a living lab. So what is a living lab? It's a building that people actually use, but one that's also been designed to generate insights, i.e. give some data, and not just provide, say, in the university context, a classroom, but also generate some data. And so at the University of Montreal, there is, some of you may know, there's a new science complex called MIL, M-I-L for short. And so here, there's a map of Montreal. I hope you can see my cursor. You're the little green dot here at Mila. If you got on a bike with snow tires and pedaled 5 minutes to the Montreal West, you would end up at the MIL campus. And you would see, if you walked there today, you would see two buildings there right now, quite large buildings, basically two wings, a 6-story pavilion and a 4-story building, around 650,000 square feet. And there's everything there. There's library, classrooms, amphitheater, cafe, offices. And right now these house chemistry, physics, biology, and geography. And this is where it's going. There's 2 more parts still yet to be built. So you can kind of see on the left and the right, the dashed in buildings there. Those are, that's the next phase that's currently being designed right now, with construction planned for the next couple of years. So that will house departments like math and stats and computer science. So several of the professors here today, like Pierre-Luc and Glenn Burseth, who I think you're going to meet in a bit, and many other great profs, they're going to be, their offices will be here. On the right side of the building here, there's also going to be a new robotics lab. So here's the twist. Well, robotics will be studied inside the building. The building itself, you can think of as becoming it's a cyber physical system. So it is this massive living sensing machine with interconnected zones and real-time data and responsive systems. Le Corbusier said the house is a machine for living in his kind of like often quoted quote. But here we have a university, and many buildings honestly are kind of, I think the future is that a lot of the buildings are these, you can think of them as kinds of, a building is a robot, but the one that we can live in, and one that we can study and learn from in this case. And so I want to dive a little bit deeper into what's going to go on at this living lab and tie it back to my research. Okay. So we're planning to instrument key systems across the building, like have temperature sensors in the indoor spaces and humidity, but also monitor the state of the ventilation system. Have sensors, for example, for CO2, for air quality, and other VOCs, which are volatile organic compounds. Remember, there's chemistry profs in these buildings as well. It's a very interdisciplinary, collaborative, like data collection effort. We can combine these kinds of sensor data streams with contextual and human scale data. So we can combine it with say the patterns of weather outside, the class schedules of the building, survey responses of, for example, you can, you could design all kinds of surveys. But now if you're like me already, your mind is already probably turning towards all the kinds of questions that you could answer with this data, maybe about performance or comfort or behavior or even equity. So this kind of data, I want to emphasize, is really needed, but it's also really rare. It's the kind of richly layered real world data set that's really hard to find, and even harder to collect sometimes. So it's exactly what we need to connect the theory and the applied stuff into the kind of work in practice parts. And here now is, so just a heads up, this slide is my most talky slide. So there's going to be a lot of writing here. But what I want to walk you through are some things that we can do with this data. So we have 3 broad areas of research here. I'll just walk you through them as briefly as I can, because there's a lot to dive into. But I'll just, if there's interest in this later, there's people in the room with you right now who are working on this building, and I'll call them out at the end so you can go pester them. So we have, think of occupants and indoor environments as an area for study. So this is really like studying how indoor conditions, things like temperature, humidity, lighting, air quality, impact the people, because we know there's studies out there now that have a link between, say, your cognitive performance, whether you're in an office or taking an exam or something, between the air quality and things like cognitive performance, absenteeism. So anyway, there's a lot there, but it's like moving beyond a simple energy metric and asking, like, what does it mean for a building to be truly supportive of the people using it? So another category is energy use itself. And so this is kind of looking at the flip side, including how people influence the building. So we talked about building influencing the people, and this is the other way around. This includes things like when people open windows or adjust thermostats or move between spaces or plug things in. And this dovetails really with the research that you've been hearing about a little bit about today, this is the research that I'm super excited about as well, is how to operate and optimize building systems more intelligently, especially through better control strategies, right? So it's where the most technical part of the system lives, but it only works well if it's grounded in the realities of people and space. So we're going to come back to this middle category on the next slide. But first of all, I just want to mention another piece that this building unlocks. And this is having feedback, because the data we collect, it doesn't just help us operate the building better in the moment. It ideally feeds back in how do we design, how we model, how we plan the future buildings. So this can help us move from assumptions that we have to make because we don't have any data to actual evidence. And that evidence can give architects, can give engineers, can give policymakers some insight into what works over time. So this is the next part of the talk, where I want to take you a little deeper into the middle category, building systems and controls, and specifically how the Living Lab could open up opportunities to rethink heating and ventilation performance. So Jean-Simon and Pierre-Luc and Vincent just gave us really, really great overviews and insights into the value of using advanced AI controllers and machine learning so we can reduce the energy use, in particular in commercial buildings. And I want to build on that. So here we have a building, I'm using the word building too much. So first of all, data, right? Most buildings aren't designed with the intention of enabling machine learning. And if you are, many of you in the room have experienced this, right? If you don't have good data, that really limits what we can learn and the questions we can ask. And so in contrast, having a living lab is intentionally instrumented to support control modeling, so we can get high resolution, multi-zone, labeled, good contextualized data streams. So that's the first thing. The next thing is experimentation. So we need buildings where we can actually test things. So testing advanced control strategies in live conditions, not just in simulation or post hoc analysis, which is how we almost always do things now. And so people are actively working towards creating zones within this living lab that can be safely piloted by the researchers just for this purpose. And I think that is really, really exciting. I've already talked to some collaborators who are pretty excited about this aspect of the building. So the third thing is smarter generalization. So what I mean is one of the biggest challenges in buildings is that you've heard of is that the models trained in one building often don't work well in another. And this is where a lot of the friction and pain comes in. And this is where my current research is focused on this generalization. So I will just give you like a few words on what I study, so you kind of have an idea of who I am, where I'm coming from. So I'm working on something called graph neural networks to help learn representations of a building. You can kind of think of them as like learning a generalized template. And the idea is, could we come up with something that out of the box would do well enough using reinforcement learning controllers applied to a new building with very little tuning? This would allow us to move from start from scratch, which we have to do, to more transferable intelligence. So I want to help controllers adapt more quickly, basically. But for that to work, we need data-rich environments like this living lab, and we need test beds where real control algorithms can be deployed and iterated on safely. Because as you can imagine, going to a building owner, even if you have an excellent algorithm, there's a lot of risk. And so, we need these kinds of we need these institutions and to support this kind of research for it to work and be deployed widely. Okay. So I've talked a lot at you. We often talk about smarter buildings. And it's true that the built environment is increasingly becoming a cyber physical system, right? Like the robot building as a robot. Think of a building a little bit like a self-driving building that can manage itself, that ultimately, this is way like down the road, but that can actually commission itself. Or I've heard someone else describe it as infrastructure with an operating system. So what we need is to keep in mind, though, that the buildings right now that we build, like we're really locking ourselves in for decades. The building itself is not, is not iterating at a cycle of every week and having a new version every few weeks or every few years. With concrete and wood and steel, we're really locked into design choices for decades. And we're not just adding AI onto buildings. We really need to rethink what buildings are and how they interact with people and how they impact the planet. So maybe what we need are kind of better systems, and not just making a building responsive, but making our research more responsive as well, so that there's better alignment. And really in the long game, we need buildings as systems that really reflect what matters. So environmental values at their cores, and putting people at the center of the buildings, which it sounds so obvious. And yet it can be really hard to do at the end of the day when you're in a room of engineers and you're value engineering these things out. But that's the long game. And I think the real potential of pairing AI with like these real-time, real-world buildings research is to help us make these better choices. So on that note, this work is really made possible by a committed group of people. There are some wonderful engineers and architects working at this building. I can't take credit for any of the actual building stuff. I'm actually just, a postdoc who's a liaison with some of the people whose names are up on the slide, like Bertrand and Pascal and Kashi, who are in the audience with you, and professors like Glenn Burseth and Eugene Siriani from UDEM. And I really want to thank my supervisors, David Rolnick and Joshua Bengio, who are supporting me and giving me the time to spend time thinking about this important topic. And thank you all for your time today. And basically, I'm happy to talk more virtually afterwards if there's a way to do that. And I'm always open to collaboration or discussion. So thank you.
Merci beaucoup. Thank you so much, Donna. We have your email address here, so if you have any questions, if you need follow-up questions, feel free to email Donna. I'm pretty sure she'll be very happy to answer them. I will invite you to a short break. We'll have 15 minutes to mingle, get a cup of coffee, cup of tea. There's still some fruits and croissant, and we'll get back at 11. Thank you. Is it working? Yes. I see that we're having a lot of conversations, and that's great. I love when I cannot even hear myself. That's perfect. But please come back to your seat. We're going to get started in 30 seconds. Thank you. And a quick note before we get started. So we will start serving lunches over there on the bar. If your laptop or bag or anything is still there, please grab it before it's covered by lunches. How was the coffee break? Thumbs up? Yeah? Great? Amazing. So now we're moving to our first panel of the day, the role of AI in grid optimization. I'm very happy to welcome on the stage Glenn Bersett, core academic member at Mila, Ad Karmanolis, Chief Executive Officer at Somo Energy, Antoine Lesage-Landry, Associate Academic Member at Mila, Vincent May, AI Researcher at Hydro-Québec, and Léo Laliberté from Local Energy. This will be moderated by Alexa Corcoran from our partnership team. Thank you very much for being there. I will let you go.
Hi, everyone. Welcome to the panel on the role of AI in grid optimization. As mentioned by Gabrielle, my name is Alexia. I work in the partnerships team here at Mila. And I'll be moderating this exciting panel today with my partners or collaborators here. In the previous presentations given by Jean-Simon, Pierre-Luc, Vincent, and Donna, we learned more about the role of and the potential of AI in reducing GHG emissions from buildings. Here, we turn our conversation or our discussion towards our power grids. In Canada, the total electricity demand is expected to increase by around 50% by 2050. To meet that increase in demand and to reach our climate targets, we need to think of our electricity systems and make them cleaner and smarter. Hence, our panel today with these 5 experts who will join me in addressing these topics. I suggest we start with so I know Gabrielle introduced you quickly, but perhaps another quick round of intros, or you can give us a bit more information, an overview of what you're doing, and especially for those who work at companies, some of us might not be too aware of the objective and the vision of those companies. So we can start here.
Yeah, thank you very much. Good to see everybody. Yeah, my name's Glenn Bersett. I'm a professor of reinforcement learning and robotics here at Mila and a core member. I've been doing a lot of kind of control algorithms, basically that work under stochastic settings and applied to real-world systems like robotics. I guess I'm here today too because at least from my view, like a power grid is a big, giant, awesome robot, also very complicated to control. And part of a bit of what work that I do is actually control systems these days for robots, but also over robots that are changing in form and designed differently. And that will be helpful in this case from what I've been discussing partly with this group here beforehand. For a while actually, is like the power grid is changing quite often. So you kind of need to figure out how to also adapt your design and optimization algorithm when new things are being added and removed quite a bit, and then being able to generalize these to other power grids of also different designs.
Thank you. So I'm Antoine Lesage-Landry. I'm an associate professor of electrical engineering at Polytechnique and also an affiliated member at Mila. So I work at the intersection of OR, AI, and power system for better planning and operation of those power system with the increasing penetration of renewables. So I'll be chatting a bit about that and about my research work as well at some point.
Hello everyone, I'm Vincent. I'm a research scientist at Hydro-Québec Research Center, where I work in the data science and AI team. And so I'm trying to, with my research, to help Hydro-Québec meet the different challenges through what machine learning can provide us or help us with.
Hello, my name is Ath. I'm the co-founder of Soma Energy. At Soma, we build AI models to deliver energy intelligence for large producers and consumers of electricity on the grid. Prior to Soma, I was an electricity trader and buying clean energy for large loads like data center. I was at AWS for 5 years, and I created the energy optimization team there that helped scale Amazon's global energy procurement program from 7 power plants to over 600 globally today. And so Soma Energy is a spin-off or built upon that success to help other consumers of electricity use AI models to make better decisions on how to harness clean energy on the power grid. Very excited to be here. I went to McGill as an undergrad in computer engineering, so I love the Mila Institute. So very nice to meet you all.
Hi everyone, I'm Leo, the founder of Local Energy Solution. I'm a Mila startup here, so very happy to be here today and present what we do in these labs right stairs away from here. But basically at Local Energy, we are also in the grid optimization, but on a different scale. We like to think of ourselves as the next brain box AI, but for a completely different sector, let's say. So we want to transform this industrial sector where there's not a lot of solutions available for them, but we see a lot of benefits for them where we could help them transition to a greener way of doing things.
Thank you to all of you. Let's kick off the conversation with a question for you, Vincent, around Hydro-Québec. So most of us know about Hydro-Québec, but we don't know really what happens in the research center and all of the challenges and opportunities that lie there. So what are the current challenges of Hydro-Québec with regards to energy production and grid stability? And how can machine learning be used to meet those challenges?
Yeah, so I'm going to start with brushing kind of a very general portrait of the challenges we have. So you can imagine that in Quebec, we use a lot of energy. Pretty much half of it is produced by Hydro-Québec, is electricity. The other half is actually fossil fuels. And so if you want to achieve the energy transition in the society, we need to shift this energy back to electricity, and that means that Hydro-Québec will have to adapt and to provide this electricity. And so that means that there's going to be maybe 2 or 3 challenges that we have to focus on. One of them is obviously increasing the power capacity, right? And so that means one, being more efficient with what we currently have. So there's a lot of work with machine learning that will need to be done on this, machine learning or other kind of approaches. It also means that we need to be to add some new sources. And these new sources, for example, will be wind turbines, and wind turbines are less easy to control than hydropower, which means also it adds a lot of complexity in the control of the system. And one also, last thing, and to refer to what we've been talking the last panels, also helping the consumers use energy a bit more efficiently is also something that is very important. But there's another condition if we want to make this transition work, is that we need our power grid to be reliable, right? Because electricity will be even more at the core of the energy provided to society. And so that means that we need to care about the different assets that we have, so the different transformers, the different things that we have in the power grid. And that's also very complex because there's a lot of them and it's a very, very complex machine. It also means that we need to be robust to extreme events, such as weather events, climate events, also to cybersecurity attacks. So there's a lot of things that are happening that we need to manage correctly in order to make this, to achieve the energy transition. And this needs to happen in a very difficult environment because things are evolving very fast. People are consuming electricity different ways. Just think about working from home. It's changed the pattern of consumption. Think now about electric vehicles that are coming. think about climate change that makes that the weather patterns, the temperature changes differently. And also climate evolution actually impacts our hydrology, impacts the winds. So there's a lot of things that are changing, a lot of uncertainty, and we need to manage all of this. So if I want to summarize, we need more efficiency, we need more robustness with something that is getting more and more complex and more uncertain. And so that's where machine learning can actually be useful, because it so happens that we also are producing more and more data. And so can we valorize this data and use machine learning to tackle some of these challenges is the question that we're asking ourselves. And so I'm going to give 3 applications really quickly that we have whether been developing, that are being developed, or we're thinking about developing. One of them that is pretty critical is predicting the demand. We've been talking about the peaks and how expensive they are and how difficult they are to manage. If we're able to predict them accurately, we're able to better adapt and better prepare. And so predicting the demand of the consumers at the next day is quite challenging. There's been a lot of research being done on this for a very long time, but now it so happens that AI systems, machine learning systems with deep learning are actually the most accurate predictors for that, and that's pretty much some of the things that we're using currently. It's been deployed. Something else that is being currently done is think about the different. One of the biggest sources of outages is actually vegetation that hits the power lines. If we're able to, and we're actually doing that right now, get 3D point clouds of all the vegetation that we have and actually identify what's the places where there's the most risk because the species of the tree, the type of, the situation of the tree. We use machine learning actually approaches to identify these, detect, and accordingly do maintenance. So that's something that is being developed. And one last thing, which is something that personally is in my research orientations, is about sequential decision making. So when we try to do optimal control of the power grid, for example, whether to balance load generation, to control voltage stability, things like this. There's a lot of challenges that come here because complexity, uncertainty, and all of this. It's been addressed for many, many years with very advanced operational research approaches, and they work pretty well. They're already, and they will struggle a bit more with the complexity and the uncertainty that are coming. So we're thinking about how can we use machine learning approaches, whether inside these current methods or using reinforcement learning more generally to try to tackle this. So that's a direction that we're going to.
Thank you for sharing all of that.
May I jump in? Absolutely. Yeah. Okay. So thank you very much, Vincent. I think we've been discussing a lot together. So of course I'm absolutely agree. And I think one of the last thing we can add with the last one is the time scale. So renewables. So here, we're very fortunate in Quebec. When we say renewables, we think of hydro, but life is very good with hydro. So let's just split renewable and say non-synchronous renewables, so PVs and wind turbines. So life gets a bit harder. And so the time scale also changed. It's much faster. And so although those algorithms on the sequential decision-making approach needs to adapt to that. So that's the one thing. But the other comment I wanted to make is something, so when we consider power system, so see how I refer to it. Okay, I guess that's my icebreaker. So we talk a lot about energy, kilowatt hour, megawatt hour, and that's very important. And we've been used to that, okay. But now that we're increasing the load, what's becoming even more important is power. So I'm thinking, you can say it's just the derivative of the other, and you're absolutely right, and I'm geeking out. But it's the instantaneous energy we can get. How much power do we have available? What's our peak? The peak demand is not related to the energy we can supply, but the power we can supply at that time. So I think that's another shift that is coming, and again, it's related to the time scale. So thinking more about power, about the efficiency of the whole system, and I'll come back on that later on, is important. So this shift of just an average over time, which is our energy, to what do we have instantaneously at this time to supply our load. I think that also goes with the change we're experiencing and that Hydro-Québec is working pretty hard on. So thank you.
Thanks for jumping in there. I wanted to ask you actually to give us a bit more information on the research that you're doing and other potential AI use cases with grid optimization. So taking that conversation kind of at a broader level, not at the Hydro-Québec specifically, but just generally speaking in grid optimization.
Yes, certainly. So happy to share the research work we've been doing. So again, I can relate to the nice introduction that Vincent provided. So one of the field that is, I believe, very rich for AI research is everything that has to do with the end consumer. So the load, the just residential load, non-residential, commercial, and so on. Because on the one hand, it's a lot of people. That means if I want to get a physics-based model for everyone, I'll just have to send a swarm of measurement people to characterize all the load. So that's merely impossible. So having a more data-driven approach, then we circle back to AI, is one way of getting good, accurate prediction for our load. And that would also allow us to not only have the aggregate model, say for a system, so say so let's say your own local neighborhood, but you could get more like the precise model for each individual load, and then from that you can build for the distribution system and so on and study different levels of impact. So a lot of modeling has to do on demand response. So in my research group, we've worked with commercial buildings, so with BrainBox AI that was named before. We've also worked with non-residential buildings, so think of actually this building would be one, but an hospital, polytechnic, everything that I guess do not have people's. Okay, no, I don't want to see these. Oh, yeah. So that do not have people living in. So that's a lot of power, and these research can be used for, on the one hand, predict how much flexibility can we tap in to balance the supply, but also something like assess the base load so that we can reward properly people that are participating to those demand response events. So if we have an approach that is robust enough that we cannot game, that becomes interesting because it balances not only the system, but also the reward that can be done. And then another interesting topic is then moving on. So I was very like low hand. And then we can go to the power system. But the power system entails other challenges. At the load level, if I make a mistake at my prediction, that's unfortunate. But if my AC is off by a bit, okay, I can live with that. But at the power system level, there's the whole safety of the network that is critical. And that's also ground for a lot of interesting research that needs to be done step by step with TSO, with system operator like Hydro-Québec, but really to get the safeguards so that we can properly use AI. Not only use a super AI, but use an AI and deploy it in a real system. So that's the kind of research on the larger scale. How can we have safe reinforcement learning or machine learning approach that we can trust? And on the lower hand, how can we have those approaches that capture all the differences from a lot of loads that can then be utilized? That's my quick or semi-quick summary. Yeah, I can talk a lot.
Thank you, Antoine. I'd love to have your perspective on what you're doing at SOMA and how you're working to making the grid more efficient.
Yeah, thank you. So I'll tie it into David's excellent opener today, is that what we're doing at SOMA is we're building application-specific AI models, largely based upon our domain knowledge of incorporating renewables with large loads like data centers. And so what we know from experience is that just contracting a renewable project, whether it's a wind or solar facility, does not necessarily guarantee offsetting of emissions for your load footprint. And so you have to be very mindful how you incorporate that with your load and consider in today's changing grid conditions to include battery storage, and then also what large loads like data centers need to do is add flexibility to their compute footprint. So we developed the models that enable this for the grid at scale across North America, and we're very focused on building smaller, smarter models to enable this flexibility. And through software, we can make the grid more efficient through incorporating more renewables, more battery storage, and avoiding the inflexible loads, which actually consume more power at peak times, which ultimately generate more GHG during peak loads. And so we're very excited about the deployment of our systems with our customers.
Thanks for sharing that. Yeah, I'll pass the mic to Leo, who's also on the software side, if I'm not mistaken. Can you share with us a bit more what local energy does, and more specifically, what peer-to-peer energy trading is, how it fits into grid optimization, how AI can help in all of this?
Yeah, for sure. I mean, thank you for this, but we hear all the time about peer-to-peer energy exchange in the electric way, right? We hear about grid optimization. There's this electric grid. We all know about it, but we believe there's a whole different grid happening here that we don't talk a lot, right? It's this heating grid. What do we do with our heat, right? And this is where it comes in with the industrial sector. I keep rambling on about this industrial sector, industrial parks, but they're important for us, right? They are accountable for 30% of the greenhouse gases globally, but there's no solution for them, right? There's no power to give them. We cannot just electrify them directly. And the biggest thing is they generate so much heat, waste heat, right? Let me give you this example with an aluminum plant, right, in Quebec. It powers its processes with electricity, right? So we need this grid, but then it generates everything else as waste heat, right? Enough heat to power 20,000 homes on a daily basis, right? But right now it's wasted. It's unvalued, goes straight up in the air, right? And we believe with our platform or solution, our goal is to have this peer-to-peer energy trading, harness this heat from one plant and sell it, give it to the neighboring plants right away, right? So this is where we incorporate this concept of local energy markets, right? And not just about electricity, but exchanging energy, any energy assets like waste heat, hydrogen, vapor, whatever it is, we can exchange it amongst neighboring plants and really gain a lot of benefits, both economically and environmentally impactful benefits, right? So for us, this is the case there. So all these solutions are amazing, and the heating sector kind of is lagging behind a little bit in the solution, right? There needs to be everything about flexibility, everything about everything that needs to be happening for the grid to live well and be innovative, right? We need to apply it also in the heating sector, right? So this is where we're trying to grasp a bit of everything that's been happening in the electricity side and make it happen in the heating sector.
I do have a follow-up question on that. So how does the heat grid, let's put it that way, how does it work in conjunction with the power grid? So I understand that the opportunities that we are seeing on the power grid side, you were saying that we kind of have to replicate them on the heat side. But how does one influence the other? How do they work together?
Yeah, great question. So there needs to be this distinction between local grid, local network with heat, and the global grid with electricity, right? So these industrial companies, they consume a lot of electricity, a lot of natural gas from this external grid, right? That supplies them, right? And on the heating side, it's always local. There's heat pumps, batteries, pipelines, boring old stuff that enables them to exchange this energy locally, right? But there's this connection that needs to happen that's not happening right now, right? Where we have peak shaving events, or Hydro-Quebec could call them and say, well, there's going to be a minus 40 degrees coming up in the next few days. You need to either shut down, lower your production and stuff like that, right? So when we take into account these types of external grid events, we can, let's say, for example, store a bit more of heat in the network, in the local network, and help with the peak shaving, help with the energy consumption with the storage, right? So this is where there's this communication is very important for them.
Thanks for clarifying that. And I think some of Glenn's research is applicable to what you're doing at Local Energy. I'd love to hear more about your research, Glenn, and how you ended up doing research in grid optimization, and then we'll see how that ties in with Leo afterwards.
Yeah, thank you. Yeah, there's a couple of overlaps, but maybe I'll focus on, so like heat and being able to capture some of these things, but you also need some infrastructure to be able to capture some of this heat. So I didn't mention it as much, well, because a large area of my research is doing robotics. So there's going to be hopefully at some point, like some more infrastructure projects to figure out how to keep up with these things, to be able to capture that stuff pretty well. And then Vincent and I have talked a couple of times of, like, one of the ways to also be able to make the network a bit more sustainable is if it can be more efficient, but also figuring out how to, like, when adding things onto the overall grid network, like, only add things that are absolutely necessary. So if you can figure out how to design still, like, where things are going to go, where power lines are going to be put in that process, then hopefully we don't need to add nearly as much to the network as we may have without the combination of, like, being able to optimize it better in a safe way, being able to trade the energy markets in, you know, a nice way to be able to distribute energy. So then that's where a good chunk of my research lately, because this group here is already doing a bunch of fantastic areas, and ideas is a little bit more on this design side, and that's also where I overlap with a handful of other people in the room for using like RL for design for molecules as well. Because it's, at least in the power grid case, it's tricky. It's not really designed well. It doesn't fit well into the easy paradigm for deep learning, where there's a fixed input vector, like an image or something like that, and one output vector, and those are both fixed numbers the whole time. But then if someone comes in and adds a power mill, then you have to like basically start from scratch learning this entire model, because the input vector has now changed, and the output vector has changed in this. So that's a kind of a unfortunate, kind of dumb simplification of the challenge there. So then a lot of the methods I've been looking into lately is, okay, trying to take advantage of even interesting forms of structure, even if the input is changing in terms of like vector and length. You might be more familiar with this type of stuff, like when you use any sort of LLM, it feeds in a sequence. So it can always be a variable length, and it gives a variable length output. So it's figuring out how to take models like these, wrap them kind of around power grid type control problems, or even in my case, just various types of robots. I've got like, I think 15 different kinds in my lab right now, but I just want to have one policy to control all of them. But it's also helpful because then they can share data across all of them. So if there's more data from more power grids, it makes this possibility to be able to generalize control over other power grids better. And then maybe even collecting data for buildings and other robots should be able to all collect that together and make kind of one giant model that's good because it can read data from all these systems and be helpful across a lot of them. And this just also is helpful too, because then if we want to figure out where should we put something in the grid, we can actually ask this model now. It's like, if I give the model this situation for adding this item, is that better or worse to be able to control? And it's because of the second problem, like even if you design something onto the grid, you also need to figure out how to control that thing on the grid. So you need to solve both of those problems at the same time to determine whether or not adding a new thing is going to be easy. And as you've all said, now adding any new thing is going to become even more complicated in the coming years as more renewables are added, things that are less predictable in their behavior.
Yeah, maybe I can jump to this, but the way we use OC and RF in what you do basically for us is this optimal control. And I think the guys at BrainBox touched point a bit before that on optimal control for these grids, right? So it's hard. One problem is it's very hard to optimally control the network in a data, I don't know, maybe a difficult data environment where we don't have a lot of data usually. So RF there is very good for us. I mean, it helps us tremendously. But one thing we'd like to touch point on is that it's not just about optimal control, but predictive control. This is where it comes in, and it's interesting for us. We're not just controlling the network in an optimal way. We're trying to guess what are the conditions happening in the next few hours, next few days, and then this is where we can start to have some predictive controls on the network and really, for example, just I touched point on it before, but where we could store energy a bit more before and then give them to them at a higher value on the next time, right? So it's a win-win for everybody. The one who sells the heat gets more value out of it. The other one lowers his energy consumption drastically, right? So having this predictive control with RL, for us, it's amazing. This is where we can really gain the most value out of things.
Thanks for sharing. It's good to hear a bit more on the research side and then how it's applied at local energy. I think we have about 5 minutes left for this for the panel before we open up to questions. I'd love to deep dive a bit more into the renewable energy, so the non-synchronous, or the ones you were referring to. I'm not sure if the term is good, but not hydroelectric, the other ones. And so I'll pass the mic to Ath. What role do you see AI playing in integrating renewable energies in our grid?
Yeah, great question. And you know, as we're seeing the news of data centers consuming more electricity, they're forecasting data centers to consume between 5 and 10% of the power grid in the future over the next 5 years. There isn't enough energy and capacity to meet that need in the US and some parts of Canada as well. So we need to add more renewable energy as one source. It's the quickest way to add energy into the system, but standalone wind or solar does not deliver capacity to the grid. And so this is where you combine it with battery storage, and then what you do is you co-optimize the wind solar batteries with the load, and then you can provide more reliable power for consumers. That orchestration renewables, batteries, and load is very complicated. In the past, it's been done by people as operators at Hydro-Quebec or control rooms, traders who are balancing contracts with the power plants. But that's exceeded the capabilities of people managing these systems, and AI is a perfect tool for processing a lot of data, forecasting capabilities, and making decisions under uncertainty. So it's really going to drive a lot of the integration of renewable energy in the future. It's going to enable more battery storage to be deployed both at the edge, both in large load centers and at data centers, or in next to power plants. And that's all powered by AI and models and a lot of the research that's been done in the past from institutes like Mila.
Anyone else want to bounce off that question? So how AI can help in integrating renewable? I feel like.
So, and I think so one of the other difference I'll be making with the modern power system is that so energy efficiency is very important, but also now system efficiency. But so that's not I don't think that's a very common wording, but it's just the way I put it to say just peak shaving. Oh, why are we talking about that? It's because we have to have the hardware to satisfy the peak. But that does not only mean the turbines or anything. It also means the power lines, the transformers, and so on. So one of those things would be to better, more optimize our way of operating the whole system so that we can operate it efficiently as a whole system. And I think AI and machine learning can be good tools to address that at the scale, both in terms of number of variables or parameters, but also the time scale.
I just want to add a bit to that too, because it's sometimes there's a bit of a tricky like false statement where it's, well, no, people aren't always quite as good at planning as we may always think we are. And in this case, it's like a really hard planning problem, partly because there's so much stochastic stuff. So but now because there's so many renewables, now we kind of like need a system that can now keep track of like thousands of things at the same time and figure out how to make a decision from that. And this is where like maybe, at least in the case from deep learning, because it could include data from the power grid, it could include data from the current weather. At some point, maybe it'll include data for like what's going on in the social network. Maybe there's an awesome like soccer game going on right now, and that's going to actually affect the power grid and needs to be predicted over. So figuring out still like good ways to ensure privacy to do this stuff too, because some of this stuff should be taken care of carefully and it is private information, but figuring out like some models and ways to modernize this to even make it possible to do this prediction, because there's things that just aren't captured in current models that are used just kind of because of design, but I'm sure they'd want them to be included.
Yeah. Let me just add one thing to that. That's a perfect point. And what we see in the power grid today is that because it's so complex, people are operating the grid very conservatively, and so we're not accessing all the energy in the grid, or we're not able to put as much renewables on the grid because we don't have the right software to manage everything. So that's a great point.
Yeah, I completely agree. I think currently the way things are done is actually a bit conservative in order to manage a lot of things. But also want to point out that electrical engineering is a very old field, and there's very smart people who have been working on this for very, very long. And so where do we come in with, as machine learning scientists? It needs to be taken with, we have a lot of things to learn. And for me, that's what's happening when I joined Hydro-Quebec. I actually come from Mila, so I come from the machine learning thing. And so there's a lot of things that I see, okay, there's a lot of methods that already exist. And so I think a very specific point is to try to find in the things that already exist, where is it that we can actually help? Where is it that machine learning is needed? And really the characteristic, and I think it goes along with what we've been saying before, is the complexity that is increasing. And the current methods will start to struggle or with that. They have to be over conservative. They will work. We're not going to run into problems, but they're less efficient. And also with the uncertainty that comes in. All this means that we have to be over conservative with the current methods. And the idea is, okay, how do we try to, with machine learning, to be a bit better? And every percentage of efficiency that we get is enormous in terms of impact, because electricity is everywhere. It's a lot of money. It's a lot of emissions. It's a lot of everything. So machine learning will not solve everything, but it can get things better, a bit better, and that's already enormous.
Great, thanks for sharing that perspective. I always love when I don't have to moderate it, then everyone just takes a mic. It means it's a good question, and you have obviously great answers. I think we could go on, but we are up on time, right? Okay. We have about 10 minutes, I think, for Q&A. So please, if you have any questions, you can use one of the 2 mics that are here.
Hi, thank you very much for the panel. I'm curious about compute and GPUs. I've been hearing more and more about that being a real limit to the growth of AI systems, and I was curious to hear, particularly Hydro-Quebec's perspective on this, whether there's a strategy in place to adapt to this new growing demand on the grid, and speaking to the entrepreneurs in the crowd, are there any sort of business ideas that you can think of for people to address this problem? Like, for instance, maybe setting up, a bank of GPUs in northern communities, and the compute all happens there, and then the results come back. Are there ideas like that maybe you could suggest?
Yeah, so I'll speak as a researcher because that's my role, and I don't know the whole strategy above me, but what I know is that we actually have been following really closely the projections about compute. Of what I understand, it's not yet something in Quebec. We see in a lot of states, for example, in Virginia, I think is one of the states that I think 50% of their power is used for that. Maybe you can support this or talk about it a bit more. But so I see that we're following it. It's things that we are aware of. Right now, it's not yet. I don't know personally about a strategy about this specifically, though.
I'd like to add, I think there should be a strategy in place to enable more compute for, say, students, researchers, to help, train models that could lead to, breakthroughs or new discoveries. I don't think there is. I'm not sure if there's even a GPU cluster in Mila. But that's something that would be very important for pushing the state of the art in research and deploying models that could be very useful to the community and society.
Maybe I'll add on to that. So far we have 3 compute clusters at Mila. One of them that just kind of kicked into gear a few days ago is actually located in Quebec City next to Laval. So there's a handful of them. But figuring out where to put them is a really tricky question, because it probably maybe would be nice to put it up north, because then you can capture the heat. But you also need to have really great bandwidth, or there's not really a point of putting the cluster there. So these, at least in Canada, tend to exist where there's power and a really good fiber optic connection to actually be able to process data and send it out back and forth really good and fast and reliable. And actually, maybe that's another way to connect this to a good question. There are a lot of similarities between the power grid problem and actually the bandwidth control problem and infrastructure that's being built in there as well. There's some of the same difficulties. I've actually been reading papers in that area lately to help give me more ideas for this particular problem, because they're dealing with the same thing. Companies like Netflix are trying to figure out, okay, how do we supply as much bandwidth to everyone and actually figure out where to store the movies that they will be streaming to people, and they will move that data around the country across servers in order to make it easier for it to supply that type of thing. It's not something you can do with electricity. You can't just kind of transport stuff, but there are some batteries for those details. And there was one other thing I was going to mention that I totally forget, so I'll just hand it off to the other excited people.
Yeah, no, so one thing to add to that as well is we're talking about all the HPC and all the infrastructure, but there's also not all applications need the big LLM to be solved and so on. So I think thinking of a model that is applied, that is dedicated to that one, that is not necessarily, say, deep learning, but we have many strategies that we can use is also part of the equation. Having solution tailored to the application as opposed to the one size fit them all that the humongous LLM can do. And I think that could also help. I mean, it goes back to my demand response example in a sense, but it can help using properly the resource we have for those specific applications. So I think there's also this that can be think of.
I want to add something really interesting. I saw a conference lately about the people from Virginia actually telling us about the impacts of these compute clusters on the power grid. And it's kind of interesting because, yeah, first of all, you need to bring more power. That's one thing, put more capacity. But then these loads, these chargers actually have a very specific behavior that are very challenging for power grid operators. So when you use them for training, you suddenly have all the GPUs that start and stop and start and stop, and that's like a lot of, it's shaking the grid a bit. And then when you use it more in inference, then it's a lot more smooth because statistically you have a lot of people that ask for it at some time. But these are very fragile equipment, very precious equipment, and so the people managing the clusters, they have security checks. And whenever there's a little bit of instability on the power grid, they just like disconnect from the power grid and they use their own power generation, which makes that suddenly the load goes down and it's a big shock again on the grid. So these are like on top of adding more power, you have other kind of impact that actually quite interesting on when you try to deploy these big clusters. I'm talking about the really big ones in a power grid. That's what's kind of interesting at the conference.
I just remembered the other thing I was going to mention. Thanks to you, so I appreciate that. So there may also be an optimization problem in machine learning right now, and so maybe some of the researchers can pick up on this. Because normally what's done right now is a model usually needs to be an order of magnitude larger only for the training process. There's something unique about handling the challenge of trying to compress so much data from scratch. The model needs to be huge, and then all the companies tend to then afterwards it's possible to compress like 99% of the information down to a model that's an order of magnitude smaller. So there will be a lot of work in this area. I do some of this for robotics because now my big giant model has to fit on a single computer in a robot right now, and that'll still be in the future, or for self-driving cars. Eventually this all needs to be compacted down to something that can operate in real time and still not consume a lot of energy. So there'll be more work there to hopefully alleviate some of these problems as another difficult thing to predict.
I just want to add something on this question of, for sure, data centers are a good subject, but let me give you some back, from the energy perspective on our point of view. Some of the numbers we've received, that was 2 years ago, right? But the Ministry of the Province of Quebec, right? They received 186 electrification projects on their tables, right? And they were only able to say yes to one, because we don't have enough power, right? So for me, the question is, I know we talk about new power, we need new power, but it's a huge issue, right? I don't know where we're gonna find this new power, right? So this is, for me, I mean, it's nice, these data centers, but we need those watts, those megawatts to come in quickly, right?
We have time for one last question. I think there's one here.
Yes, thank you for the panel. We've heard a lot about day-to-day grid optimization, and now we have all these great algorithms. I assume they sometimes leads to a decision on what kind of new infrastructure is needed. But do you find it easy this infrastructure is going to be there for decades, so do you find it easy to use those grid optimization into like new climate conditions in the future so that we make sure the new infrastructure is not maladapted to the new climate in a few decades from now?
Yeah, so it's a very important problem. So there's two things there that I see. First one, will the algorithm that we're developing fit what's going to happen in the future? That's one question, and these are both for classical algorithms and machine learning. We have to adapt them, okay? But I think that's not exactly the question you ask. It's more like, will the infrastructure that we develop and we install, will it be reliable given the different changes that are coming? And right now, it's part of the test that we do. Like when we think about deploying new infrastructure, we actually plan under different scenarios, and we try to test if it will work. Yeah, so we for example, plan, okay, what if I have this profile of consumption over a year, like in 2050, and I have installed these wind turbines at this place, and there's some wind, and at some point there's no wind for 1 week, and have this and this and this and this. Okay, and now I run for a whole year, try to see what's going to happen on my power grid. Will my power grid hold? So we do this kind of test, and actually machine learning can help also to do this kind of test to increase the speed of these simulations, to improve the control that we simulate during this 1 year, for example. So we try to use algorithm there too, but for sure we have to do this test because things are changing, things are evolving. As I was saying, there's a lot of uncertainty coming in with the climate change especially, but also just the growth of society in general. So in all of this, yes, we need to do these tests, and we do them.
I'll I guess keep adding on where I think a part of maybe a key for the future is also just having a larger industry for robotics. Basically, we're not very good at adapting, and especially infrastructure changes. So like even for the last question, like maybe it would be great to have like a giant compute server up north, but we can't have the bandwidth there. But what if that actually wasn't hard? To be able to do that stuff, to be able to change these infrastructure. I feel, okay, it wasn't the best place to put this particular item. We're actually quite terrible at relocating stuff, and that might not even work. And often it's more expensive to relocate something than it would be to build a new thing and not even use the old thing. So we're pretty terrible about basically maybe industrial level recycling and being able to change these areas. And that's a really key big reason why I get into robotics, and at least for me, hoping to build up a lot of the robotics infrastructure to be able to support these types of questions and make these proposals much cheaper to be able to reuse some of these objects and adjust things faster.
So yeah, my turn to get to around this question. So there's a few aspects I want to touch with that. So on the first hand, there are work that has been done, that is ongoing, and see one of the things that is changing for planning is, I think typically we were planning with on-load, on-peak, off-peak, shoulder, and that was it. And that was just a study we were doing with kind of 3 data point over 25 years, and so on and so forth. But now studies are more shifting toward much more profile, so that not only do we test our system, is it big enough in a sense, but will it make it through the system? If I load and overload and load and underload my transformer, will it age well? So that is the kind of thing that are going on. But that, as you can see, if I'm making a simulation for 25 years and I'm having a data point for every hour of my 25 years, that's a lot of things to crunch. And so that's why combining all those approaches, optimization, machine learning, and more AI can help. And then, so that would be maybe my answer to the reliability part of the question. So, can we sustain? Can we supply power on a daily basis? How can we characterize the energy we're not supplying? But then moving on to another aspect, which is much, much harder, is resiliency. So major event, extreme weather condition, and that's much harder because we're talking about a framework that is based on data, but that is very scarce data that we have on that, so that's there need to be tailored approach for that. So this is going out of my field, so I'll kind of stop here, but that's another very important approach, another subfield that needs to be investigated, extreme weather condition, and how can we plan according to that, because very quickly there's the trade-off of being absolutely robust, so I'm overbuilt, but then maybe I'm wasting some capacity, but also what is the cost of losing power for a week? And I think we have a very good example, and I actually conclude with that. Those past 2 spring, we had events that were major. In Montreal, maybe I'm Montreal-centric, but we had something like freezing rain at one time and just very heavy snow, and the distribution system was out for a few days. So these are the extreme weather events I'm talking about, and that also needs to be included, which is much harder than the reliability, which I think is progressing well. So that was my summary. Yeah.
Vincent, 30 seconds.
Yeah, so very quickly on this weather extreme events, actually they are very hard to predict with physical-based weather models, and we are looking at seeing if machine learning models for weather forecasts, which are being running out very, very quickly lately, could be better, for example, to predict ice rain, to predict wind gusts very locally. These are some topics that we're interested in to looking at also.
Thank you. I think our time is up. Huge thank you to all of you for joining us today for this important discussion.
Merci infiniment. Thank you so much for this excellent panel. It was amazing to hear you all. By a show of hand, who's hungry? Who's starting to feel a bit hungry? Me too. I see someone clapping. We still have one last panel, one last but not least, and I promise you it's worth the wait. I'm also hungry, but let's dig into material discovery for energy systems. And I will invite Kulbir Kaur-Kuman from INRS, Bruno Rousseau from Mila, and Donna Shaban-Kabakibo from Mila as well, a panel moderated by Alex Hernandez Garcia. We can maybe do a round of applause for them. We'll close this morning together. Please take a seat.
Right, hello everybody. So everybody's hungry and we have to deal with this now. So I hope you bear with us and stay in your seats despite the hunger. So yeah, we're going to talk about energy systems and materials discovery for this kind of problems and challenges. We have an amazing team of panelists here, so I would like to briefly introduce them and let them introduce themselves too. So, Donna, you're a PhD student in physics. Do you want to introduce yourself to the audience?
Hello. Hello, my name is Donna. I'm a PhD student in physics at Université de Montréal. I work in condensed matter field, which is the study of how atoms behave when they get close enough to each other to form liquids or solids, and how that affects their properties, thermal, electric, magnetic, etc. I work on the simulation level, so I simulate those materials on a computer rather than conducting experiments in a lab. So, yeah, thank you for having me.
Thank you, Donna. Bruno is a senior research scientist at the Applied Machine Learning Research Lab here at Mila. Do you want to say a few more words? Thanks for being here.
Thank you for having me. My background is also in condensed matter physics. That's the field I got my PhD in. But then about 10 years ago, I shifted gears and I went towards more like data science. And I joined Mila 5 years ago. I joined the AMLER team. Our focus is really to try to bring all the great ideas that are developed by our academic community and try to help companies deploy these ideas for their own problems. So I think this is a great background to have. It gives me perspectives on both sides of material discovery and AI.
Thank you, Bruno. And last but not least, we have Kulbir with us. He's a professor at INRS and Canada Research Chair in Computational Materials Design for Energy and Environmental Applications.
Thank you, Alex. Very sorry that we are standing between the lunch and you guys. I'm Kulbir, as Alex mentioned, and I would also like to say that I'm a condensed matter physicist. I was a condensed matter physicist. I did my PhD in that, but after that, I met chemists and material scientists in University of Toronto. So I worked with them for a few years on CO2 conversion to fuels and chemicals. So I was designing catalysis. And then after that, I had the opportunity to work in Japan and Switzerland, where I mainly focused on materials used in fuel cells and batteries. And I'm here at INRS since 2019. And currently, we work on mainly designing materials, but for applications go from catalysis to CO2 capture to fuel cells and batteries.
Great, thank you. And yeah, I'm Alex, by the way. I'm an assistant professor at the Université de Montréal and a core faculty member here at Mila and member of Ivaro and Institut Courtois also. Yeah, this is very exciting. Like we said, we're going to talk about energy systems. And my plan is to try to get an overview from the panelists about energy systems, what are the challenges, and then move towards understanding why materials are important in this case, and then how and why AI could be used for these problems, and also discuss some of the social implications of potential impacts of this work. So maybe to try to be all on the same page, Kulbir, could you give us an overview, like a brief overview? Of course, this is a difficult question of energy systems. What are we talking about when we say, what do we mean by energy systems in this case, and why this is important? Some picture of some challenges.
Absolutely. So energy systems, when we think about energy systems, we think how we produce energy, but actually it's way more complicated. It's a network of processes, devices, infrastructure that comes under energy systems, and it's not just how we produce energy through maybe renewables, fossil fuels, but how we distribute energy, how we consume energy in houses, in industry, in transportation, and how we store energy. That has become a very important point in order to have the sustainable energies in these times. So storage, production, consumption, and how we generate energy, these all come under energy systems. And why is it important? Well, about 70% of GHG emissions come from energy systems. How we are generating energy, how we are consuming, that affects the climate, and that's what we are trying to fight right now, the climate change. So it has a huge impact on current days, the most important problem that we are all trying to deal with, that is climate change.
Thank you. And Dunia, so part of your work during your PhD is focused on batteries and battery materials. So maybe to try to get a little bit into the details, can you give us a picture of why this is an important topic to work on for you in particular? What is maybe the role of batteries in the energy systems?
Yeah, so first of all, on a broader level, since we're trying to shift our energy systems into more sustainable sources, this means that we're going to have intermittent sources of energy like wind, solar. And for those to be able to be used, we need efficient energy storage systems. So it's important to build more and more well-performing energy storage systems. On a more specific level regarding transportation, which is one of the biggest sources of greenhouse gas emissions, if we're looking to electrify our transportation systems, we need better batteries, and we need to improve those batteries. So that's more my focus right now, is batteries that could be used in cars, for example, electric cars.
Okay, so it seems, this is a big topic, a lot of ground to cover. I would like to move towards trying to understand why materials and discovering new materials as well can play a role in addressing some of these challenges we're talking about. So maybe Bruno, you have some experience in this area with an understanding as well from both the physics, the material science, and the artificial intelligence side. So I would like to understand. What is the role of materials in, for example, batteries, but not only? Maybe you can give us some other examples, and why discovering new materials specifically can be an interesting approach for the future.
Yes. So the world around us, the technological world around us, is why we have the quality of life that we have today. The various technological artifacts that we have are all powered by underlying physical principles, right? But these must be embodied in physical things. So we need materials to embody these physical principles. And certain materials will perform better than others, right? And since we never only want one thing from our materials, right? We always want our materials to perform many things. We want them to be cheap, we want them to be abundant, we want them to be easily recyclable. And so there comes a need for our society to really try to optimize our choices, right? So right now we're producing energy in large part using fossil fuels, which led us to this climate crisis. And so now we want to shift away to other approaches. And so there's a big need to find better materials to serve the same old functions that, say, fossil fuels have served so far. And so that's really where the game is. We know what we want, but we need to find the combination of atoms that will deliver the function that we seek, right? And that's a very challenging endeavor, but also a very rewarding one, right?
Thank you, Bruno. Yeah, I would like to hear some more examples, and maybe, I don't know if you, Kulbir or Dunya have...
Sure.
Feel free to add to this.
Everything around us is made of materials, right? And this table was not in this form. Probably there is an alloy involved in here, which doesn't exist in nature by itself, right? We invented it, we made this more sturdy, maybe more lighter, I don't know. So steel is another example. Now everything is made of steel, so that was not there before. It was invented at some point. So if I go a little bit deeper into my research, so what we are trying to do, for example, for CO2 capture, right now the way we capture CO2 in power plants is using pressure and swing operations, pressure and temperature swing operations, which need a lot of energy. So what we are trying to do, because the materials are not efficient, in order to absorb CO2 and then desorb CO2, we need energy. And what if we have a material that doesn't need that energy, right? Then we are indirectly not only just capturing CO2, but also helping the environment by not using that energy. So we need a new material. Similarly, in catalysis, there are several reactions we work on: conversion of CO2 to fuels, ammonia synthesis. If you think about green revolution in around 1920s, we wouldn't have the food that we have right now that we're going to eat in the lunch if it was not for green revolution. Green revolution happened when we invented Haber-Bosch process, where we first time realized that, okay, we can use iron to do this reaction to produce ammonia, which can be used in fertilizers. So now we have fertilizers, now we have food, there's plenty of food, and otherwise our population would have reduced to 50% or something like that. So now right now the problem with that Haber-Bosch, really almost a century-old process, is that the iron that we invented at that time is now producing carbon dioxide. The carbon dioxide footprints of ammonia synthesis process, Haber-Bosch process, is about 2 gigatons, and it uses about 3 to 5 percentage of natural gas. So now we are trying to look for a material that can replace iron because it's not sustainable. So again, now we need a material that can do this reaction at lower temperature, because currently iron needs more temperature to do this reaction. We need an earth-abundant material, we need a cheaper material, we need a material that is non-toxic. So all these qualities have to be present in one material in order to solve this problem. So we cannot escape that. Evolution in technology comes through, is directly connected with materials, whether it is fuel cells, batteries, lithium-ion batteries. Nowadays we work on sodium-ion batteries as well. I worked a lot on fuel cells as well, where we used to have these Toyota Mirai cars in Japan standing next to our department, and anybody could use it. But a lot of people didn't have those cars. The reason was the materials used in that fuel cells were very expensive. So the car will run for 25 years. I don't know right now the capacity, but after 25 years, you have to discard the car. And it is very expensive to buy at the first place. So we need to replace the material, specifically platinum, that was used in polymer electrolyte membrane fuel cells. Because platinum is rare, it's very expensive, we cannot sustain that. So what material can mimic platinum? So what we do in AI, computational world, and experiments is try to, using the fundamental properties, intrinsic properties of materials, we design new materials by mixing them together, by creating defects, by making interfaces, and so on. There are different strategies to do that so that we can discover new materials and therefore have more sustainable technologies.
Yeah, thanks so much. It's great to actually hear some specific examples and this great overview. For example, how it is actually connected to the carbon emissions in some of these electrochemical reactions in industry. Dunya, I don't know if you want to tell us some details specifically about batteries and why we need new materials for this problem in particular.
Yeah, so as I said, batteries play an important role if we want to shift towards more sustainable energy systems. And I'll take again the example of transportation. So for example, the current batteries used in electric cars weigh about half a ton, which is a lot. So our work is to aim to find better solutions for batteries, is specifically looking for new materials that would replace the current electrolyte used in batteries, that is liquid, by a solid one. So the electrolyte is the material that separates the two opposite parts of a battery, and it allows for the transportation of lithium ions. So if we can find a solid candidate for an electrolyte, that will allow the battery to be less heavy, more compact, and also safer, since when maybe you've seen some pictures of electric cars catching fire, when there's a damage to the battery, it's usually this electrolyte that catches on fire. So a solid electrolyte would make the battery safer in that sense.
Thanks. Okay, so we need new materials for a bunch of applications, apparently. Hopefully this is clear by now. So yeah, why don't we just, make some? And so why is this hard? Bruno, can you maybe, and of course the rest after, but can you help us understand why this is a pretty complicated thing to do, discovering new materials for specific applications?
Yes. So at a fundamental level, a material is composed of three things. The atoms, of course, the composition, namely the ratios of each kind of atoms, and then the shape that these things take in space. How are the atoms arranged in space, right? And so the relationship between that fundamental description of a material and its function, the properties it has, is highly non-trivial. It's very hard, even for an experienced chemist, to just look at a chemical formula and immediately know, oh, this is going to be a great catalyst, or this is going to be a great material for a PV panel, right? And so looking for new materials that have the properties we desire is like looking for a needle in a haystack. And it's an exponentially large haystack, right? The periodic table is very large, and even if you remove undesirable elements such as uranium or the very heavy elements from the moves you can play in this game, you still end up with a very, very large space of possibilities. And ultimately, it's very difficult, because even if you come up with a composition, I would like to try this compositions of elements, there's no a priori guarantee that you'll be able to synthesize it, right? It takes a lot of expertise and a lot of know-how to even make milligrams of something new, right? And then you have to characterize it. Does it have the properties that we want? We already have, say, a large database or historical knowledge on a lot of materials, but that's, let's say, a hypothetical database is very sparse, right? You may have a material that is well known and it's been used for 100 years for, I don't know, conducting electricity, but no one maybe bothered looking whether this material was also good for some other new application, right? So even though we know a material exists, we don't necessarily know all of its properties. And so it's very much a time-intensive, labor-intensive process to identify a new good candidate for a given application.
Yeah, thanks, Bruno. So, Kulbir, you actually have a great focus in your work on really trying to work on materials that you can experimentally measure and characterize experimentally and so on. So maybe you can tell us more about this and to give a picture of how hard this is, how time-consuming it is to characterize a material and so on.
Yeah, I will continue my ammonia story. So, so as probably you now know why ammonia was important, we are since ages we are trying to replace iron that is currently being used in ammonia synthesis process. So when I was in Japan, I thought, okay, well, let me start this project, and that was my first attempt on designing a material, new catalyst for ammonia synthesis. And we thought theoretically it makes sense to mix iron with ruthenium, because ruthenium has a very nice properties. Maybe we can make a non-toxic system, and that works efficiently, less temperature, and so on. So that was our guess. We started with there. We did some experiments. We did some theoretical calculations. We could make a new catalyst that was non-toxic, that works better than iron, but has efficiency issues and is expensive. So it couldn't go to the market, right? And after 3 years, that project took 1.5 years. We did a lot of experiments, a lot of tests and everything. I came back to Canada and I said, well, what is there in Canada that is abundant? Let me mix copper and nickel. So they're abundant, let's just mix them and see if they can be a better catalyst because of some intrinsic properties we thought. It took us another 1 year to identify, well, it will not work either. So now we wasted 2 years. Well, we published papers, they're good papers, they're good fundamental papers, but it's not applicable. Those materials cannot go to the industry right now. So now, after doing all that, after wasting about 2.5 years, we thought, well, how many materials could be possible? If we just think about 38 transition metals that are there in the periodic table, how many times we can mix them? And what are the possibilities, right? If we mix different compositions, 50% of copper, 50% of nickel, 60% of copper, 40% of nickel, and then mixing more than 2 metals, there are a million possibilities to design those materials. And that is very hard. It's hard to even do that computationally, theoretically, and it's even harder to do all those tests experimentally and expensive, and it needs a lot of infrastructure and time, which we don't have. Right? If we want to solve the climate change problem in coming few years, we don't have that time. That's where AI is very useful. I have a lot of points over there, where and when it can be used. But it is a hard problem to discover a new material. It's a labor intensive, as was mentioned by Bruno. It needs a lot of infrastructure, and there are millions of possibilities to discover new materials. Back in the day, the materials, some of them that you know happened by accident. We don't right now have time for those accidents to happen. So we cannot continue on this path and invent something new very quickly because it's very time consuming.
We cannot rely on serendipity given the climate crisis. Right, so you've mentioned AI already, and it seems like it might be a suitable tool for this problem of the needle in the haystack that Bruno was mentioning. So maybe let's discuss a bit more about this. What are the ways in which machine learning, AI, if you will, can help us navigate this vast chemical space, potentially accelerate the characterization of the properties of materials in a way that can assist the scientists in the field. So it would be nice to get and delve a little bit into these questions. I don't know. Yeah, Bruno, go ahead.
So, as you mentioned, we can no longer rely on serendipity, right? And maybe not the next, but another thing that's been tried is high throughput, right? I don't want to just try a few things here and there. I want to scan broadly, but as was previously discussed, turned out that this is also very difficult because that search space is enormous. The latest edition, if you will, on this problem, or the latest iteration is inverse design. Instead of trying to look through a large haystack of potential candidates and measuring them all one by one and try to find an interesting material that satisfies our needs, inverse design instead says, let me specify from the beginning what property I desire. Say, for example, I'm looking for a new material for a catalyst. Let me predefine the redox potential that I require for my application. And then I will use AI to generate, much like ChatGPT will generate a sentence when it's prompted, can I have an AI model that will generate a new material with these properties, right? And so that's very exciting. The golden path or the shining path, the ideal long-term solution would be to have something like such a generative model coupled to an automated lab, something that could basically run 24/7 and try new compositions informed by the AI model, but also feeding back information. We tried this composition, it doesn't work, here's some new information, try again. And if we could accelerate this loop, then the hope is that we could go to new material much more quickly. The challenge right now is that creating an automated lab is highly challenging. So what's being done a lot right now is you have these generative models, but it's very difficult to feed those models with the properties we're looking for. Typically in material science, data sets are very small, right? You don't have internet scale data. You only have a handful, hundreds of experiments in the literature. And simulating those properties can be very challenging. If you go beyond band gap and stability, if you want to, for instance, look for ionic conductivity in a new electrolyte, that can be very, very challenging to simulate. And so that's the Achilles heel right now, getting those properties.
Yeah, I agree. I love that. Yeah, so you mentioned ionic conductivity. Let's hear about it. Dunya, do you want to share the specific example you're working on solid state batteries, solid state materials? You want to find new materials that have high ionic conductivity. Can you tell us more about this and specifically how you're using machine learning models to tackle this problem?
Yeah, so as I said, the goal of the project is to find new candidates for solid electrolytes for lithium batteries. And the project involves multiple steps. First of all, as Bruno mentioned, there's a lack of data generally in material science field. And so the first step of the project was to build a data set of solid electrolytes that we know of and for which the ionic conductivity was measured in a lab. So ionic conductivity is a measure that tells you how well the electrolyte conducts the lithium atoms, lithium ions. And then so that this is done, it's not a huge data set, but at least we have something to start off. And the second step is to develop an AI model capable of predicting ionic conductivity for unseen materials that will be trained on that data set. Because, as you mentioned, it's very difficult to predict those properties in a lab or even on a computational level. If you're going to do physics-informed calculations, they could take hours or up to days. So if you want to scan a lot of materials at a time, we need to develop a model that is quickly able to tell me how good or bad my new candidate is. So this is the second step of the project. We're still working on it. Third step is to train a second AI model, which is a generative model capable of generating new candidates, and it's going to have under the hood the first model that I talked about that will be able to inform that model how to generate those candidates so that it's able to generate generally good, possibly good electrolytes. And I think the next steps of the project are as challenging is how we need to test those materials in a lab, and then the battery is not just made of an electrolyte. There are other components, and you need to make sure that this electrolyte is compatible with the other components, and there could be defects in those systems that could affect the performance. So many elements to keep in mind, and I think that's one of the biggest challenges in those projects is to be able to bring all game players together and make them work together on this multidisciplinary project so that it works.
Thank you. So time is flying, at least for me. I don't know if that's the case for the hungry audience too. So before opening up for questions, I would like to end here with a bit of a discussion about, ethical, social implications of all this. We're talking about innovation on AI, discovering new materials, batteries, new fuels, meeting energy demands, storage, etc. That's exciting from a technological and scientific point of view. But to me, at least, it raises questions about, extractivism, like mining of materials, and then it makes me think of, for example, here in Canada, the impact this has had on indigenous communities, displacement, access to water. We have the example of the extraction of lithium for batteries of cars in South America, for example. This has a dramatic effect on the access to water of the local communities. So I know these are difficult questions and we don't have a lot of time, but what are the maybe other challenges that come to mind, things that are important that we keep track of and that we are aware of. And if you have solutions or personal approaches that you put when you think of these problems, and if you want to share, I think it would be interesting to hear for me and hopefully for the audience too.
Go first. So I think that's definitely one of the biggest challenges we face, and it's important to focus on the sustainable materials in that case. The materials that we can rely on for, well, not any material is like forever sustainable, but there are certain materials that silicon, carbon, that we can use, and if we can incorporate them more into the technologies, that would be really remove this issue. For example, another way is to really think about the critical materials, critical minerals, and use them very carefully. Back, I think 2 or 3 years ago, NSERC had a funding call on using critical materials with industry partners. So that was fantastic to see what critical minerals are there in Canada and how can we use them responsibly. And third thing that I would like to say is we should focus on recyclability as well. There's a lot of material that are present in our electronics and that can be recyclable. We use phone for a few years and then we destroy it, and sometimes not properly, and use another phone. And the materials that are used in each of our phone, they are, first of all, humongous amount of materials and they are precious. So can we focus more on recyclability to have that circular economy? Last thing that comes to my mind is it's very important to involve community. So when it comes to mining and other issues, it's important to get their feedback, the people who are not scientists, but they are getting affected by them. So that's a very important point that we should do.
Thanks so much. Go ahead.
Yeah. I think I totally agree with all the points that you mentioned. I would like to add one extra thing in the sense that I think as researchers we need to have in the back of the mind how our research could impact the future of the world, and how to look for new materials that are sustainable, that would lead to more performing batteries, for example, which means using less materials. But at the same time, I think there's an urgent need to try and shift our mindset of how we think about energy and about our consumption of energy. I think the goal is not to consume more and more energy, because I think this is not sustainable, even if we find best solutions ever to store energy and produce energy. If we want to, if we're aiming for carbon neutrality by 2050, there's no way this is going to work even with very good technology. I think there's an urgent need to shift our mindset, in policy making, in day-to-day life, for all of this to work together. And it's important for researchers to communicate the right information to the public so that this shift can happen in reality. So it's the responsibility of everyone, including researchers.
Yes, I agree. Maybe to give you a specific example, a lot of lithium-ion battery materials have critical materials in them, such as cobalt or nickel. And these, of course, are very contentious materials. There are alternatives. One material that is, I think, was developed locally, or at least was researched heavily by Hydro-Quebec, is lithium iron phosphate. It only has iron and phosphate, no nickel, no cobalt, right? It's perhaps less performant with respect to certain metrics, but it's much more sustainable. It still has lithium, so of course there's still work to be done. But I think one strength of material science research is bringing a lot of alternatives to the table. We don't have a single material for this application. Here's a bunch, right? But it becomes a social choice, right? Which material are we going to actually use at scale, right? And so material science and AI can provide help, but they in no way remove the need for society and responsibility, and for us to make the right choices, ultimately. They're not a crutch, they're just an accelerant for our good decisions.
Thank you so much. I really appreciate these thoughtful comments to end this discussion. And yeah, before we close it, I would like to welcome questions from the audience. like before, feel free to come to the mics. No questions. So maybe I have a question. Oh, Glenn, thank you.
Well, no, thank you very much. And partly because I'm interested in this area, but Alex and I still haven't managed to find the time to talk nearly enough, which is kind of typical of the life. But you also seem to have a lot of knowledge about like the AI systems that are being used like in this area, but also the limitations. So you mentioned some for lack of data. I was going to phrase this question in kind of a more mean way for like, how come we haven't discovered all these yet? But then, so like, what is maybe the one more like active thing you can work on like more recently to help address this? Like, is it a data problem? Is it a model problem? Is it a priors for the model problem? Which one of these is like the worst culprit right now?
My opinion is, yeah, of course, all of the above in various ratios. I think data is like, it's always the data, right? It's like it's the economy, stupid, it's the data. I'm very excited to see, for instance, big tech companies enter this space. For example, Open Catalyst from Meta, right? They've created a very, very large data set that takes a big chunk of the subtlety of the problem into consideration, right? It's not just 300 data points, it's a very large database. It's still simulations. Ideally, this would all come from the lab, from experiments, but I think it's a step in the right direction. I think since material science is really, must be grounded in the real world, we must make measurements, we must go to the lab. So I'd say it's really we're data constrained. Great models will come once we have the right data, I think.
Absolutely, I completely agree. Data is one of the biggest challenges we have. In order to discover new materials, if we even have to scan through these different compositions and different materials to synthesize them, characterize them, it takes years. So we don't have enough data to train those models. So if you ask me whether AI is helpful for material science, not always because of that. So we must stick to some of the traditional techniques because sometimes those are more useful than doing AI on a very small data set. And why are we not generating enough data? Well, as the Meta guys, they have developed a lot of catalysis data, but it also changes with the problem, right? If I'm working on, for example, I was looking into the data and I was working on CO2 capture, and there was data on different, same material, all the alloys, but not for CO2, but for hydrogen, nitrogen. So it just needs a lot of exponential amount of resources to generate that data. And for each material science problem, we need a certain kind of data. I also worked on solid oxide fuel cells where when you go into the nanoscale, there are several grain boundaries and interfaces present in these fuel cells. And even 1 micrometer chip will have like thousands of grain boundaries. And these grain boundaries are supposed to, they lower the efficiency of the fuel cell. Now, how do we understand them? Can we do TEM for each one of those grain boundaries? I think a person will sit in a lab for the next 10 years to do just 1 micrometer chip and do the TEM images. And it needs a very specific expertise. So right now, it's not possible to get real data from experiments. But we can definitely get data from simulations, but even that is time consuming.
Sorry. Is there any particular maybe experiment or material where it's not so hard to generate data? Because a lot of the open window for language or for models has been language has been something where we have a pile of data, even though visual stuff is where we have a lot more just piles of it laying around. But that allowance of having language gave us some more capabilities, we presume at the moment.
Absolutely. I think simple materials, like if you think about metals, probably you'll find data on them, not the complex systems, but also the techniques. For example, depending on the problem, let's say Raman spectroscopy is fairly easy to do as compared to TEM, transition electron microscopy. So that data is very scarce, but Raman spectroscopy can be done very easily, and in a weekend you can generate a lot of data. So there are ways to use techniques that can generate a lot of data in less time, but do they solve the problem? It depends on the problem.
Yeah, like is that data also would need to be helpful for other problems? Like it's sort of like, is there a place to gather enough fundamental information about how like physics and chemistry evolves from a cheaper experiment to collect data?
Maybe to add to this, I think there's a lot of opportunities for automation. There's a difference between a sleep-deprived postdoc running these experiments by hand and perhaps a whole battery of robots doing it. Right? I think there's a bright future for automated labs. I think we're at the beginning of this, and I think I see the future more along the lines of let's identify a very interesting problem and let's build the infrastructure around that problem, not just very large generic databases for any problem, but let's specifically focus on one application and let's just build a bunch of robots. Maybe that's a dream for the future, but I think you don't just need data. You need data around a well-defined problem. Then you repeat that over and over again from application to application.
Thank you.
Thank you, Glenn. I think it's lunchtime, right? So. Yeah, thanks for the appreciation. Thanks, Colbert, Dunia, Bruno, for this nice panel, and yeah, I hope it was informative, especially for those of you who haven't thought so much about this kind of problem. And yeah, enjoy the rest of the day. Enjoy the lunch.
Merci. A few last words before you get up. I know we all want to go for lunch. Thank you very much for this panel. Thank you for being with us this morning. It was a great session. My job here is done. It was a pleasure to be with you. We're going to have another session this afternoon, and I strongly invite you to come back at 1:30 for topics related to biodiversity, forestry, etc., and finance, climate finance as well, very important to fund all the projects we've been talking about. Thank you again for being with us. I will let you take a lunch here. You can eat here or in a co-working space, which is just over there. Just take the corridor here, and you're going to find it very easily. Merci beaucoup.